Nobody tells you the real reason we cannot reach the stars. They show you the concept art, the fictional warp drives, the Hollywood shortcuts. But strip all of that away, and what you are left with is a truth so staggering that most people would rather not hear it. What if the universe was never meant to be crossed? If you are someone who genuinely loves this kind of content, make sure to give this video a like. Now let's get started. Let's start with something nobody puts in the headline. The problem with interstellar travel is not that we lack a fast enough engine. It is not a funding problem. The problem is that the universe has a specific set of rules. Here is the one that stops most people cold when they actually sit with it. To move any object faster, you need energy. That is obvious. The faster you want to go, the more fuel you need. But fuel has mass. And mass requires more fuel to move, which has more mass, which requires more fuel. The equation does not grow steadily, it explodes exponentially. The faster your target velocity, the more the fuel requirement balloons into something that stops resembling engineering and starts resembling absurdity. Physicists have calculated what it would take to reach even a modest fraction of the speeds needed for interstellar travel using conventional propulsion. The fuel mass required does not just exceed what we could carry. It exceeds the total mass of every star, every planet, every atom of observable matter in the known universe. That is not a way of saying it is hard. That is the universe saying no. But even if you solved the energy problem entirely, you still have not solved the thing that most people never think to ask about. You have not solved time. Not in the science fiction sense, in the biological sense, because interstellar distances are not just large in terms of kilometers, they are large in terms of years, decades, centuries. And the human body was not built for that, not even close. Bone density degrades in microgravity, the immune system drifts, muscles atrophy, cognitive function changes in ways we are still studying. And on top of all of that, quietly, invisibly, constantly, the galaxy is firing high-energy particles in every direction, leftovers from dying stars. And in the open void between solar systems, there is nothing to stop them. No magnetic field, no atmosphere, just you and radiation that current shielding cannot fully block, accumulating damage across a journey measured in human lifetimes. Every solution you reach for creates a new problem that loops back to the same wall. And that wall is not made of metal or money. It is made of physics. Now, we are going to explore some of the more exotic ideas people have proposed to get around these energy barriers, from nuclear pulse propulsion to light sails to antimatter engines. And some of them are genuinely fascinating. But before we do, I want you to sit with something. We are only at the beginning of this story. We have covered distance and energy, and already the scale of the challenge should be making your mind spin a little. Because here is what is incredible about this moment. Every single one of these barriers we are talking about was figured out by human beings, regular people with curious minds, doing math with pencil and paper or with telescopes pointed at the sky. The fact that we even know how far the stars are, how much energy it would take to reach them, what the rocket equation says, that is one of the greatest intellectual achievements in the history of our species. And now we are going to go even deeper. The universe is more creative in its obstacles than any science fiction writer has ever imagined. And we are just getting started. The stars are almost incomprehensibly far away, and that the energy required to reach even the nearest one at a meaningful fraction of the speed of light is so enormous it breaks conventional propulsion entirely. But scientists and engineers are not people who give up easily, and over the past several decades, some genuinely brilliant minds have proposed alternatives, ways to cheat the energy problem, ways to push past the limitations of chemical rockets and get something, or someone, moving fast enough to make interstellar travel at least theoretically possible. Let's walk through the most serious of these proposals, because they deserve to be taken seriously, and because understanding why even these ideas fall short tells you something profound about the universe we live in. The first big idea is nuclear pulse propulsion, and honestly, of all the concepts ever proposed for fast interstellar, or at least deep interstellar precursor travel, this one might be the most grounded in real, tested physics. The concept goes back to a project called Orion, which was developed in the United States in the late 1950s and early 1960s. The idea was straightforward in its audacity. Detonate nuclear bombs behind a spacecraft, one after another, and use the shock waves to push it forward. A massive plate at the back of the ship, called a pusher plate, would absorb each explosion and transfer the momentum into forward thrust. Studies suggested that an Orion-style spacecraft could theoretically reach speeds of around 3 to 5% of the speed of light. That is genuinely impressive. At 4% of the speed of light, you are looking at roughly 106 years to reach Proxima Centauri. Still more than a human lifetime, but not by an absurd margin. With a multi-generational crew, or with advances in human longevity, you could begin to imagine it. But here is the problem, and it is not an engineering problem, it is a political and environmental one. The Partial Nuclear Test Ban Treaty of 1963 effectively killed Project Orion before it ever got off the ground, detonating thousands of nuclear weapons in space, or worse, in the atmosphere during launch, is not something the international community was or is willing to accept. And practically speaking, building enough nuclear warheads to fuel such a mission would require a stockpile that dwarfs anything currently in existence. So Orion, as magnificent as the concept is, lives in the realm of the theoretically possible but practically forbidden. The next serious contender is nuclear fusion propulsion. Rather than exploding fission bombs, a fusion drive would use controlled thermonuclear reactions, the same process that powers the Sun, to generate thrust. A project called Daedalus, designed by the British Interplanetary Society back in the 1970s, laid out a detailed blueprint for a fusion-powered spacecraft that could reach Barnard's star about 6 light-years away in roughly 50 years of travel time. That is remarkable on paper, 50 years, within a single generation, but here is the catch. We do not have controlled nuclear fusion. Not yet. As of today, we are still working on it. Facilities like the ITER project in southern France, the largest experimental fusion reactor ever built, are making genuine progress. In December of 2022, the National Ignition Facility in California achieved fusion ignition for the first time in history, meaning they got more energy out of a fusion reaction than they put in with their lasers. That was a monumental achievement celebrated by physicists around the world, but achieving fusion ignition in a laboratory setting under extremely controlled conditions is a very different challenge from building a compact, reliable fusion engine that can run continuously for decades in the hostile environment of deep space. Most experts believe practical fusion power is still several decades away on Earth. A space-ready fusion drive is likely further still. We are getting there, but we are not there yet. And not there yet, when you are talking about interstellar travel, means we are potentially still generations away from even having the engine, before we even begin to address every other problem on the list. Then there is the idea that captured the imagination of the scientific community and the public, perhaps more than any other: the light sail, or more specifically, the laser sail. The concept is elegant. Instead of carrying your fuel with you, which is the core problem of the rocket equation, you leave your fuel source at home. You build an enormous, gossamer-thin reflective sail, attach it to a tiny spacecraft, and then blast it with a powerful laser from Earth or from orbit. The photons from the laser push against the sail, accelerating the craft. No fuel needed on board, no rocket equation death spiral. The most serious modern incarnation of this idea is the Breakthrough Starshot initiative, announced in 2016 by a group that included the late Stephen Hawking and funded by the Russian entrepreneur Yuri Milner. The plan involves launching a fleet of gram-scale spacecraft called starships, each attached to a sail just a few meters across, and accelerating them to 20% of the speed of light using a ground-based laser array with a combined power output of around 100 gigawatts. At 20% of the speed of light, the journey to Alpha Centauri would take about 20 years, and then another 4 years for any signal sent back from the spacecraft to reach us. So roughly 24 years from launch to receiving the first data. Within a single human lifetime. It is a genuinely thrilling concept, but let's look at the engineering. 100 gigawatts of laser power focused on a tiny sail over a distance that grows from 0 to millions of kilometers in a matter of minutes requires a level of precision and infrastructure that does not currently exist anywhere on Earth. The total global electricity generation capacity of the entire planet is around 8,000 gigawatts. You would need to dedicate more than 1% of all electricity produced on Earth just to fire this laser. Building and coordinating that infrastructure is a challenge at a civilizational scale. And then there is the sail itself. At 20% of the speed of light, even a single dust grain in interstellar space hits your spacecraft with the energy of a small explosive. The sail and the starship need to survive that bombardment for 2 decades. The materials science required to build something that thin, that light, and that durable does not yet exist. Breakthrough Starshot is not science fiction. It is serious science being pursued by serious people. But the gap between the concept and the reality is measured not in years but in decades of fundamental research and development. And now we arrive at arguably the most underappreciated obstacle of all. One that does not get nearly enough attention in discussions about interstellar travel, maybe because it is not as visually dramatic as a warp drive or as conceptually thrilling as a wormhole, but it might be, in practical terms, the single most dangerous barrier we face: radiation. Space is not empty. We tend to picture it that way, a vast, dark, silent void, but it is filled with radiation. And the further you travel from the protection of the sun's magnetic field and the Earth's magnetosphere, the more exposed you become. There are 2 main sources of radiation that an interstellar crew would face. The first is galactic cosmic rays. These are high-energy particles, mostly protons and atomic nuclei, that have been accelerated to extreme velocities by supernova explosions and other violent events across the galaxy. They stream through the cosmos in all directions, constantly, relentlessly. They are moving so fast and carry so much energy that they can punch straight through metal, straight through water, and straight through human tissue. On Earth, you are protected. The planet's magnetic field deflects most cosmic rays, and the atmosphere absorbs most of the rest. Even on the International Space Station, astronauts receive a radiation dose roughly equivalent to about 8 chest X-rays per day, which is manageable for short missions but begins to accumulate dangerously over months. NASA's guidelines currently limit career astronaut radiation exposure to levels that correspond to a no more than 3% increased risk of fatal cancer over a lifetime. Now consider that an interstellar journey, even at an optimistic fraction of the speed of light, would take decades. Some scenarios involve centuries. The accumulated radiation dose from galactic cosmic rays over that period would be, by current understanding, lethal. Not eventually might cause cancer lethal, lethal in the more direct sense. The second source is even more unpredictable. Solar particle events, massive eruptions from stars that blast enormous quantities of energetic particles outward in all directions, even traveling away from our own sun. you would still be exposed to similar events from other stars as you travel through the galaxy. And in interstellar space, with nothing to shield you, a major particle event could deliver a fatal dose in hours. Shielding is the obvious answer, but shielding heavy enough to actually protect against galactic cosmic rays at the levels required for a multi-decade journey would be extraordinarily massive. And mass, as we discussed in part 1, is the enemy of speed. Every kilogram of shielding you add to the spacecraft is more mass you have to accelerate, which requires more energy, which requires more fuel, or a more powerful laser, which adds more mass. And around you go. Some researchers have proposed using magnetic shielding, generating a powerful magnetic field around the spacecraft to deflect charged particles, similar to the way Earth's magnetosphere works. It is a fascinating idea, and studies have shown it could work in principle. But generating and maintaining a magnetic field strong enough to provide meaningful protection over a decades-long journey requires enormous amounts of power and technology we have not yet built. And it does not protect against neutral radiation like gamma rays and neutrons. There is no clean solution on the table today. Every option involves trade-offs that cascade into new problems. Here is what makes this all so extraordinary, though. Every one of these barriers, the energy requirements, the propulsion limits, the radiation environment, was figured out not by aliens, not by some advanced civilization millions of years ahead of us, by us, by human beings, using telescopes and particle detectors and equations written on whiteboards. We mapped the cage from the inside. And that is a staggering achievement, because knowing the cage exists, knowing its exact dimensions and the nature of its bars, that is the first step toward finding the door. And in the next part of this video, we are going to talk about something that physicists have been wrestling with for decades. Something that sits right at the intersection of general relativity, quantum mechanics, and the kind of ideas that sound like pure science fiction until you look at the actual mathematics. We are going to talk about what happens to space, time, and the human body when you approach the speed of light. And we are going to look at whether the universe's ultimate speed limit is truly unbreakable, or whether there might be a loophole hiding in Einstein's own equations. Because if there is one thing the history of science has taught us, it is that the universe occasionally rewards the people who refuse to accept that something is impossible. If you are enjoying this journey, make sure to give this video a like and subscribe. Every video I bring you the latest from astronomy, astrophysics, and cosmology, explained in a way that actually makes sense. Albert Einstein was 26 years old when he turned physics inside out. Working as a patent clerk in Bern, Switzerland, with no university laboratory, no research team, and no prestigious title, he published 4 papers in a single year, 1905, that collectively changed everything we thought we knew about the nature of reality. Physicists still call it his miracle year, and the most consequential of those papers, the one that sits at the very heart of our conversation today, introduced the world to the special theory of relativity. Most people have heard of it. Far fewer truly understand what it says, and what it says about interstellar travel is simultaneously the most beautiful and the most brutal thing in all of physics. So let's walk through it together carefully, because this is where the story of why the stars are unreachable gets genuinely strange. Special relativity is built on 2 foundational ideas. The first is that the laws of physics are the same for every observer, no matter how fast they are moving. The second, and this is the one that breaks your intuition, is that the speed of light in a vacuum is always exactly the same, regardless of how fast the source of that light is moving, or how fast the observer is moving. That second postulate sounds almost boring until you chase its implications, because it means that light does not behave like anything else in the universe. If you are standing still and someone throws a ball at you from a moving car, the ball's speed relative to you is the car's speed plus the throw speed. That is how everyday objects work. Velocities add together, but light does not do that. If a spacecraft moving at 90% of the speed of light turns on its headlights, the light from those headlights does not move at 90% plus 100% of the speed of light. It moves at exactly 100% of the speed of light as measured by any observer anywhere. To make that mathematically consistent, to make the universe work so that everyone always measures light at the same speed, something else has to give. And what gives is our intuitive understanding of time and space. Time is not constant. Space is not rigid. They bend, stretch, and compress depending on how fast you are moving. And the faster you move, the more dramatic the effect. The consequence of this that is most relevant to interstellar travel is called time dilation, and it is not a hypothesis or a theory that has yet to be tested. It is a measured, confirmed, experimentally verified fact. GPS satellites have to account for relativistic time dilation in their calculations. Without those corrections, your navigation app would be off by kilometers within a single day. Here is what time dilation means in plain terms. The faster you move through space, the slower you move through time relative to someone who is stationary. Let's make this concrete. Imagine a spacecraft accelerates to 90% of the speed of light and travels toward a distant star. On Earth, observers watch the journey and measure, using all available instruments, that the trip takes 10 years. But the crew on the spacecraft, living, breathing, aging, experiences only about 4.4 years. The clocks on the ship run slower, their heartbeats are slower, their cells divide more slowly, they age more slowly. Not because of any trick or illusion, but because time itself is actually passing more slowly for them. Plilv the speed higher, and the effect becomes more dramatic. At 99% of the speed of light, for every 7 years that pass on Earth, only 1 year passes on the spacecraft. At 99.99% of the speed of light, the ratio becomes even more extreme. In principle, you could travel to a star tens of thousands of light years away and arrive having aged only a few years on board. This sounds like a solution, and in a narrow technical sense, it is a solution to the problem of human lifespan. If you can get close enough to the speed of light, you personally could travel vast distances without dying of old age on the way. But, and this is a colossal but, it does not solve the problem of getting there in the first place. The people back on Earth still experience the full journey time. A signal sent back home from your spacecraft still takes years to arrive. The civilization that launched you continues to age and change while you travel. You might arrive at your destination having aged 5 years, only to return home and find that 200 years have passed. Everyone you knew is gone. Everything has changed. You are a time traveler in the most isolating sense imaginable. And more fundamentally, time dilation only helps you if you can actually reach those extreme velocities to begin with. Which brings us straight back to the energy problem we discussed before. Because approaching the speed of light does not just require a lot of energy, it requires an infinite amount. This is where special relativity delivers its most devastating blow to interstellar travel dreams. As an object with mass accelerates toward the speed of light, something strange happens to its relationship with energy. The faster it moves, the more energy you need to accelerate it further. Not in a linear way, in an exponential way. The closer you get to the speed of light, the more the energy requirement explodes upward. As you approach light speed, the energy required to go just a tiny bit faster approaches infinity. What this means in practice is that no object with mass can ever reach the speed of light. Not because we have not figured out the engineering yet, not because we need better materials or a bigger reactor, but because the universe itself prohibits it. It is written into the mathematical structure of space-time. Mass and the speed of light are fundamentally incompatible. Light can travel at light speed because photons, particles of light, have no rest mass. Everything that has mass is locked below that cosmic speed limit forever. This is not a wall we can engineer our way through. This is a wall built into the architecture of reality. Now, here is where a lot of science communicators stop. They lay out the barrier and leave you with a kind of resigned wonder, but I think that is only half the story. Because Einstein's equations, the same equations that impose the speed limit, also contain something unexpected, something that theoretically, at least, might offer a way around the rules rather than through them. In 1994, a Mexican physicist named Miguel Alcubierre published a paper that sent a ripple through the theoretical physics community. He had found, working entirely within the framework of Einstein's general theory of relativity, a mathematical solution that described something extraordinary, the Alcubierre drive, a warp drive. Not in the hand-wavy science fiction sense, but as an actual mathematically valid solution to Einstein's field equations. The concept works like this. Instead of accelerating a spacecraft through space, which runs into the mass-energy barrier, you warp the space around the spacecraft, you compress space in front of the ship and expand space behind it. The ship itself sits inside a bubble of flat spacetime and does not technically accelerate at all. It just rides a wave of distorted space like a surfer riding a swell, and because it is space itself that is moving, not the ship, the cosmic speed limit does not apply. Space has no speed limit. On paper, this is extraordinary. The ship could travel faster than light without anyone aboard ever breaking the laws of physics locally. No infinite energy requirement for the spacecraft itself, no time dilation of the extreme kind. You leave, you arrive, and the time elapsed is whatever you choose it to be. For a few years, this was treated as a delightful mathematical curiosity. Elegant but probably irrelevant to reality, like many solutions to Einstein's equations that describe spacetimes that cannot actually exist. But then Harold Sonny White at NASA's Johnson Space Center began examining Alcubierre's math more carefully, and in 2012, he announced that he had found modifications to the original geometry that dramatically reduced the energy requirements. Alcubierre's original design required an amount of exotic energy roughly equivalent to the mass energy of the planet Jupiter, converted entirely into a specific form of negative energy. White's modifications brought that requirement down by many orders of magnitude, though still to levels far beyond anything we can produce. The deeper problem is not just the energy, it is the word exotic. The Alcubierre drive requires something called exotic matter, matter with negative energy density. This is not antimatter, which is well understood and has been produced in laboratories. Exotic matter with negative energy density is a theoretical construct. We have some tantalizing hints that quantum effects can produce negative energy in tiny fleeting quantities. The Casimir effect, for example, produces a measurable negative energy between two closely spaced metal plates. But whether negative energy can be produced and maintained at the scales required for a warp bubble is entirely unknown. Most physicists consider it extraordinarily unlikely. And in 2021, a group of researchers published a paper in the journal Classical and Quantum Gravity that delivered another blow. They demonstrated that any physically consistent version of the Alcubierre drive, one that obeys all known energy conditions, cannot actually travel faster than light. The geometry, when you impose physical constraints on the exotic matter, collapses back below the speed limit. The warp drive, at least in its Alcubierre form, remains a solution in search of a physical mechanism. Beautiful mathematics, no known path to reality. There is another idea that comes up in virtually every discussion of faster-than-light travel, and it deserves an honest treatment here. Wormholes. A wormhole, technically called an Einstein-Rosen bridge, is a hypothetical tunnel through space-time connecting two distant points. It was first described mathematically by Einstein himself and his colleague Nathan Rosen in 1935 as a feature of the equations of general relativity. On paper, a wormhole could connect Earth to a point near Alpha Centauri, and the journey through the tunnel might take seconds rather than years. Here is the honest assessment of wormholes. They are mathematically allowed by general relativity. They have never been observed. There is no experimental evidence that they exist. And the theoretical analysis of their stability is deeply problematic. A traversable wormhole, one you could actually travel through without being destroyed, also requires exotic matter with negative energy density to hold it open. Without that exotic matter, a wormhole would collapse almost instantaneously in a time frame far too short for anything to pass through. The same exotic matter problem that haunts the warp drive haunts wormholes. Moreover, Stephen Hawking and others argued, in what became known as the chronology protection conjecture, that quantum effects would always conspire to prevent the formation of stable, traversable wormholes, because such structures would potentially allow travel back in time, creating paradoxes that the laws of physics seem fundamentally unwilling to permit. None of this means wormholes are impossible. Absence of evidence is not evidence of absence. But it does mean that wormholes, as of everything we currently know, remain in the category of mathematical possibilities rather than physical realities. They are not a solution we can reach for, not today, possibly not ever, and so we arrive at a remarkable place in this conversation. We have now walked through the barriers of distance, energy, propulsion, radiation, and the speed of light itself. We have looked at the most serious proposals physics has to offer: nuclear drives, laser sails, warp geometry, wormholes, and in each case, we have run into walls that are not made of ignorance or lack of imagination. They are made of the fundamental laws of the universe. But here is the thing that I keep coming back to, the thing that I think is the real takeaway from all of this. Every single one of these barriers was discovered by people who were trying to understand, not to limit. Einstein was not trying to prove interstellar travel was impossible. He was trying to understand the nature of light and time. The rocket equation was not written to discourage dreamers. It was written to describe reality as accurately as possible. And history has a long, humbling record of things that were once declared physically impossible, later turning out to be possible when our understanding deepened. Heavier than air flight, nuclear power, gravitational wave detection, the direct imaging of a black hole. Each of these was at some point considered beyond reach. The question is not whether the barriers exist. They do. The question is whether our current understanding of physics is complete. And the honest, thrilling answer to that question is almost certainly not. In Part 4, we are going to go somewhere really unexpected. We are going to talk about what the universe itself might be telling us through dark matter, dark energy, and the deepest unsolved mysteries in modern cosmology about physics we do not yet understand. Because if there is a door in the cage, it is almost certainly hidden inside one of those mysteries, and we are also going to talk about something closer to home, something that does not require exotic matter or warp geometry. A proposal so ambitious and so grounded in real physics that some of the world's most serious scientists are actively working on it right now. Something that reframes the entire question of interstellar travel in a way that might genuinely change how you think about the future of our species. Here is something that should genuinely stop you in your tracks. Something that does not get nearly enough airtime in mainstream science conversations. even though it sits right at the center of everything physicists are wrestling with today. We do not know what most of the universe is made of, not in a vague, hand-wavy, there's still a lot to learn kind of way, in a very specific, quantified, deeply uncomfortable kind of way. When astronomers and cosmologists look at everything they can observe, every galaxy, every star, every cloud of gas, every planet, every atom of ordinary matter that has ever been detected by any instrument ever built, all of that adds up to about 5% of the total energy content of the universe. 5%. The remaining 95% is divided between two things we have never directly detected, never produced in a laboratory, and never fully explained. About 27% is something called dark matter, an invisible substance that does not emit, absorb, or reflect light, but whose gravitational effects are unmistakably real. We can see its fingerprints in the rotation of galaxies, in the bending of light around galaxy clusters, in the large-scale structure of the cosmos itself. It is there. We just cannot see it or touch it or explain what it fundamentally is. The remaining 68% is something even stranger. Dark energy, a mysterious property of space itself that is causing the universe to expand, not just expand, but accelerate in its expansion. Every second, the fabric of the cosmos is stretching outward faster than the second before. The galaxies beyond our local group are receding from us at speeds that will eventually, billions of years from now, carry them permanently beyond our horizon. Space itself is growing between us and them faster than light can cross it. We discovered dark energy in 1998 when two independent teams of astronomers studying distant exploding stars, Type Ia supernovae, expected to find the expansion of the universe slowing down due to gravity and instead found it speeding up. The discovery was so shocking, so contrary to every expectation, that it won the Nobel Prize in Physics in 2011, and more than 2 decades later, we still do not have a satisfying explanation for what dark energy actually is. Now, why does this matter for our conversation about interstellar travel? Because it tells us something profound about the state of our knowledge. We live in a universe where 95% of what exists is unknown to us, where our best, most rigorously tested theories, general relativity and quantum mechanics, are both spectacularly successful within their domains, and yet are fundamentally incompatible with each other at the deepest level, where the equations that govern the very small and the equations that govern the very large refuse to be reconciled into a single coherent framework. This is not a small gap. This is not a minor footnote in an otherwise complete textbook. This is a chasm at the very foundation of physics. And the history of science tells us that when you find a chasm like that, something extraordinary is waiting on the other side. Every major revolution in our understanding of physics, Newtonian mechanics, electromagnetism, quantum theory, relativity, did not just add to what we knew. It restructured the entire framework. It changed what questions were even worth asking. And each revolution opened up possibilities that were literally inconceivable before it arrived. We are, right now, standing at the edge of what might be the next great revolution. The search for a theory of quantum gravity, something that unifies general relativity and quantum mechanics into a single coherent description of reality, is arguably the most important unsolved problem in all of science. String theory, loop quantum gravity, causal set theory, these are all attempts to find that unified description. None of them is complete. None has yet made a prediction that has been definitively confirmed by experiment, but when that unification comes, if it comes, and most physicists believe something like it must, it will almost certainly reveal properties of space-time that we currently have no language to describe. Properties that might, just might, include mechanisms for manipulating space or time in ways our current physics declares impossible. This is not wishful thinking. This is the pattern of scientific history, applied honestly to where we stand right now. The James Webb Space Telescope, which began its science operations in 2022, is already beginning to reveal cracks in our models. Galaxies that should not exist at the distances and ages Webb is finding them, fully formed, massive, surprisingly mature galaxies appearing in the early universe far earlier than our best simulations predicted. Astronomers are not panicking, but they are paying close attention. Because anomalies like these are often the first whispers of physics we do not yet understand. The Event Horizon Telescope, the global network of radio observatories that produced the first ever image of a black hole's shadow in 2019, and later imaged the supermassive black hole at the center of our own Milky Way, is testing general relativity in the most extreme gravitational environments known to exist. So far, Einstein's equations hold up remarkably well, but scientists are watching for deviations, because any deviation would be a clue, a thread to pull on. The LIGO and Virgo gravitational wave detectors have opened an entirely new window on the universe, one that does not rely on light at all, but on ripples in spacetime itself. Since the first detection in 2015, they have observed dozens of mergers between black holes and neutron stars. Each one is a test of our theories. Each one teaches us something about how spacetime behaves under the most extreme conditions imaginable. We are building better eyes, better ears, better instruments for interrogating the universe. And with every improvement in our ability to observe, we inch closer to the anomaly, the inconsistency, the inexplicable measurement that might be the doorway into a new physics. But let's be honest with ourselves for a moment, because intellectual honesty is one of the things that makes science worth trusting. The possibility of new physics is not a get-out-of-jail-free card for interstellar travel. It is a genuine possibility, not a certainty. The universe is under no obligation to contain a loophole just because we want one. The laws of physics might simply be what they are, and the barriers to interstellar travel might be permanent features of reality, rather than temporary obstacles to our ingenuity. And if that is true, if the speed of light is truly unbreakable, if exotic matter cannot be produced at scale, if wormholes are forever unstable, then the question of interstellar travel transforms into a different kind of question entirely. Not, how do we go, but how do we send something meaningful across the void? And here is where the conversation takes a turn that I find deeply fascinating. Because some of the most serious scientific thinking about humanity's long-term future does not involve sending human bodies to the stars at all. It involves something more abstract, and in some ways more profound. Think about what makes you, not your atoms. Those are replaced continuously throughout your life, not your physical form, which changes decade by decade. What persists across time is something more like a pattern, a structure of information encoded in the arrangement of your neurons, your memories, your personality, the connections between your thoughts and experiences. Now, I am not going to stand here and tell you that mind uploading is around the corner or that consciousness is simply a matter of information processing. That is a deeply contested philosophical and scientific question, and anyone who speaks about it with certainty in either direction is overstating what we know. But I will tell you that some serious people, including researchers at institutions like MIT Oxford and various national laboratories, are exploring what it would mean to send information across interstellar distances rather than matter, not the clumsy, energy-hungry business of accelerating atoms to relativistic velocities, but transmitting a signal, a coherent beam of light or radio waves carrying something, a message, a blueprint, perhaps eventually something more, because here is the thing about a signal. A signal travels at the speed of light, which is the fastest thing there is. A signal has no mass to accelerate. A signal does not need food, water, air, or shielding against radiation. A signal is immune to the rocket equation. The METI debate, that stands for Messaging Extraterrestrial Intelligence, is one of the most fascinating and ethically complex conversations happening in science right now. Because before we can seriously discuss sending signals to other stars, we have to grapple with whether we should, whether announcing our presence to the cosmos is wise, given that we have no idea what else might be out there. Stephen Hawking, until his death in 2018, was notably cautious on this point. He drew an analogy to the arrival of Europeans in the Americas, a meeting between a technologically advanced civilization and a less advanced one that did not end well for the latter. Others argue that any civilization capable of interstellar travel would already know we exist from our radio emissions, which have been leaking into space for over a century. The debate continues, but if information is the key, if the signal is mightier than the spacecraft, then the Voyager probes offer a poetic coda to think about. Both Voyager 1 and Voyager 2 carry golden records, literal gold-plated copper discs encoded with sounds and images from Earth, music, greetings in 55 languages, the sound of rain and surf and wind, photographs of human beings and cities and landscapes, a message in a bottle thrown into the cosmic ocean. Carl Sagan, who was instrumental in designing the golden records, described them as Earth's gift to the cosmos, a declaration that we existed, that we were curious, that we looked up at the stars and wondered. Those probes are now in interstellar space, moving slowly, almost absurdly slowly by cosmic standards, but moving. And the records they carry will almost certainly outlast our civilization, our species, our sun. In 5 billion years, when the sun expands into a red giant and swallows the Earth, those golden records will still be drifting through the galaxy, still carrying the sound of a mother's first words to her child, still carrying Bach and Beethoven and Chuck Berry, still carrying the mathematical language we used to say to anyone who might find them. We were here and we were listening. That is not nothing. That is, in a way, a form of interstellar travel that has already happened. But we have not yet talked about something that sits even more squarely in the middle of the practical conversation, something that does not require new physics, does not require exotic matter, does not require mind uploading or golden records, something that generations of engineers and scientists are beginning to lay the groundwork for right now, with real materials and real mathematics, the idea of a generation ship. And the concept is at once the most straightforward and the most ethically complex proposal in all of interstellar travel. Because a generation ship does not ask you to solve the energy problem, or the speed problem, or the time dilation problem. It simply acknowledges them and says, fine, we will take as long as it takes. We will build a world that travels. But the ethical questions that arise when you actually examine the generation ship concept in depth are some of the most challenging questions humanity has ever been asked to confront. Questions about consent, about identity, about what we owe the people who will be born and live and die on that ship without ever choosing to be there. Questions that do not have easy answers. And that is exactly where we are going in part 5, because here is what I want you to sit with as we head into that conversation. Every barrier we have discussed so far has been physical: energy, distance, radiation, the speed of light. But the barriers we are about to explore are human. They live inside us, in our biology, our psychology, our ethics, our social structures. And in some ways, those barriers are more interesting, because they tell us not just about the nature of the universe, but about the nature of what we are. You are made of atoms forged in the cores of dead stars. Literally. The carbon in your cells, the iron in your blood, the oxygen in your lungs, all of it was created in stellar nucleosynthesis and scattered across the galaxy by supernova explosions billions of years ago. You are, in the most literal sense, a child of the cosmos. And the fact that you are sitting here, contemplating whether your descendants might one day return to the stars, that is one of the most astonishing things in the known universe. Part 5 is coming, and it is going to make you think about what it means to be human in a way you might not have expected from a video about astrophysics. Let's talk about the generation ship. Because of all the ideas humans have ever seriously proposed for reaching another star, this one is simultaneously the most achievable in terms of known physics and the most troubling in terms of everything else. It does not ask the universe to bend its rules, it asks us to bend ours. And that turns out to be a far more complicated request. The basic concept is straightforward enough. If we cannot go fast enough to reach another star within a single human lifetime, we build a vessel large enough and self-sufficient enough to sustain a population of people across multiple generations. The first generation is born on Earth, chooses to embark, and spends their lives aboard the ship. Their children are born in transit, their grandchildren, their great-grandchildren, and somewhere down that line, perhaps 100 years into the journey, perhaps 500, perhaps 1,000, depending on the destination and the speed achieved, a generation of people who have never seen Earth and will never see it again arrives at another star. That is the plan in its simplest form. And on the surface, it sidesteps all the hardest physics problems. No need for exotic matter, no need for near light speed velocities, no need for warp geometry, just engineering, biology, and time. But the moment you start filling in the details, the complications cascade in every direction at once. Start with the engineering. A generation ship is not a spacecraft in any conventional sense. It is a world, a closed, self-sustaining biosphere that must reliably support human life, not for months or years, but for centuries. Every system aboard has to be not just functional but redundant, repairable, and adaptable across timescales that dwarf anything we have ever engineered. Think about what that means in practice. The air recycling systems, the water purification systems, the food production systems, all of them must run continuously for hundreds of years without access to spare parts from Earth, without the ability to call in a repair crew, without any external supply chain of any kind. Every component that fails has to be repaired or replaced using only the materials and expertise available on the ship itself. The agricultural systems alone represent a staggering challenge. A crew large enough to maintain genetic diversity. We will come to that in a moment, probably numbers somewhere between a few hundred and several thousand people. Feeding them entirely from closed-loop agriculture, with no soil from Earth, no natural sunlight, no seasonal variation, across centuries of operation, requires a level of biological and agronomic engineering we have not yet demonstrated anywhere. Our most advanced closed ecological life support experiments, like the work done at NASA's Kennedy Space Center and the European Space Agency's Melissa project, have made meaningful progress. But the longest continuous closed-loop life support experiments have run for months, not centuries. The materials the ship is built from will degrade. Metals fatigue, polymers break down under radiation, electronic components fail. A civilization on Earth can mine new materials, develop new technologies, adapt to changing circumstances. A generation ship carries only what it launched with, plus whatever its inhabitants can synthesize or fabricate from those original resources. The engineering philosophy required is unlike anything in human history. Not build it well, but build it to last forever, with the assumption that everything will eventually break, and plan accordingly. Now let's talk about the biology. And this is where things get genuinely complicated in ways that most popular discussions of generation ships simply skip past. The human species maintains its genetic health through a process of genetic mixing across large populations. When populations become too small and too isolated, a phenomenon called genetic drift begins to distort the gene pool. Harmful recessive mutations, the kind that are normally diluted and suppressed in large, diverse populations, begin to accumulate. Inbreeding depression sets in. Fertility rates drop, disease susceptibility rises. The population becomes increasingly fragile over successive generations. Geneticists who have studied this problem in the context of generation ships have arrived at estimates for the minimum viable population needed to maintain long-term genetic health. The numbers vary depending on assumptions and the duration of the journey, but many studies suggest a founding population of at least several hundred genetically diverse individuals is necessary to avoid serious genetic deterioration over a multi-century voyage. Some more conservative estimates push the number into the thousands. A recent study published in the Proceedings of the National Academy of Sciences examining the population genetics of a hypothetical multi-generational voyage to Proxima Centauri b, a potentially habitable planet orbiting our nearest stellar neighbor, suggested that a founding population of around 10,000 people would be needed to maintain robust genetic health over a journey of several centuries, accounting for expected mortality rates, birth rates, and the inevitable loss of genetic diversity through random drift. 10,000 people on a spacecraft for centuries. The International Space Station, to put that in perspective, has a pressurized volume of roughly 930 cubic meters and supports a maximum crew of 7. Scaling that to 10,000 people for an indefinite multi-century voyage requires a vessel of an entirely different order of magnitude, something closer in scale to a small city than to any spacecraft ever imagined. The mass of such a vessel, and therefore the energy required to accelerate it to any meaningful fraction of the speed of light, is almost incomprehensibly large. We are back in the territory of the rocket equation, and the numbers it produces for a 10,000-person city ship are even more staggering than what we encountered earlier. Some researchers have proposed getting around the population problem through a different approach. Rather than sending 10,000 living people, send a much smaller crew, perhaps a few hundred, and supplement the genetic diversity by carrying a vast library of frozen embryos or even just frozen genetic material in the form of sperm and egg cells, which could be used to introduce new genetic variation into the population at intervals throughout the journey or upon arrival. It is a creative solution to a real biological problem, but it introduces its own cascade of complications, ethical, psychological, and practical, that we will come back to shortly. Then there is the psychological dimension, and this is the one that I think does not get nearly enough serious attention, because you can solve the engineering, you can solve, at least partially, the genetics, but the interior life of human beings trapped in a closed environment for centuries is something we understand far less well, and the consequences of getting it wrong are not broken machinery or depleted gene pools. They are something more intimate and more devastating. Human beings evolved in open environments, under open skies, with seasons and weather and the constant sensory input of a living, changing world. We are social animals designed by millions of years of evolution for small tribal groups, but also for the possibility of leaving, of exploring, of moving on. The option to go somewhere else, even if you rarely exercise it, is deeply woven into the fabric of human psychology. Remove that option entirely. Place people in a sealed metal world where every wall is a wall, where the horizon is a curved corridor, where the sky is a lighting system on a timer, where the outside is lethal vacuum, where leaving is not an option under any circumstances, and you have created a psychological environment that has no precedent in human history. Even our most extreme analogues, submarines, Antarctic research stations, long-duration spaceflight, are finite. The crew knows there is an end. There is a date when they go home, on a generation ship. For most of the people aboard, there is no going home. There is no end within their lifetime. There is only the ship, always the ship. The same corridors, the same faces, the same recycled air, the same artificial light, day after day, year after year, decade after decade, until they die aboard it. Studies of isolated, confined environments, submarine crews, Antarctic winter over teams, ISS astronauts consistently show that after a certain period, psychological deterioration begins, sleep disruption, irritability, conflict, depression, and a phenomenon researchers call the third quarter effect, a dip in morale and performance that occurs when the end of a mission seems far away in both directions. Imagine the third quarter effect for a journey measured in centuries. The social structures that would develop aboard a generation ship over multiple generations are impossible to predict. What starts as a crew with a mission could evolve across 100 years into something with its own culture, its own mythology, its own power structures, its own interpretation of what the mission even is. The descendants of the original crew might not share their ancestors' commitment to the destination. They might develop factions, they might make decisions, political, reproductive, technological, that the original planners could never have anticipated. There is a haunting term that sociologists use for this: cargo cult science. The risk that knowledge, specifically technical knowledge critical for operating the ship, becomes ritualized over generations, performed without true understanding, like a ceremony whose original meaning has been lost. The people turning the dials and reading the instruments might not truly understand what the dials and instruments do. And in a spacecraft that requires precise technical operation to keep everyone alive, that is not a philosophical concern. It is an existential one, and now we arrive at the ethical question, the one that I find most genuinely difficult, and that I think deserves to be held up in the light rather than passed over. The children born on a generation ship did not choose to be there. Let that sit for a moment. The adults who board the ship, the first generation, are making a choice, perhaps the most profound choice a human being can make. They are voluntarily leaving Earth forever, committing the rest of their lives to a journey their bodies will not survive long enough to complete. That choice, however extreme, is theirs to make, but their children have no such choice. They are born into the ship, born into a world with walls, born into a mission that was decided before they existed by people who could not ask their consent because they did not yet exist to give it. They will live their entire lives aboard that vessel, age and love and grieve and dream within its boundaries, and die without ever having breathed unfiltered air or felt rain or seen a horizon that did not curve back on itself. Is that ethical? Can the generation that chooses to board a generation ship make that decision on behalf of all the generations that will follow? Philosophers have been wrestling with variations of this question for decades, and there is no consensus. Some argue that being born into the ship is no different from being born into any constrained set of circumstances: poverty, a remote village, a culture with limited options, and that a life lived fully within those constraints is not less of a life. Others argue that the deliberate, engineered imposition of a lifelong confinement on people who never consented is a form of harm that no purpose, however grand, can justify. The physicist and philosopher George Dvorsky has written extensively about what he calls the bootstrapping problem of generation ships, the fundamental impossibility of getting consent from the very people whose existence depends on the decision being made without their input. It is a problem with no clean solution, only trade-offs that each of us has to weigh according to our own values. Some researchers have proposed that advances in human biology might dissolve this ethical knot before it ever needs to be tied. If human lifespan can be dramatically extended through genetic therapies, nanotechnology, or other interventions, then perhaps a single generation could survive the entire journey. The people who board would be the people who arrive. No forced inheritance of a decision they did not make. Work on the biology of aging is genuinely progressing. Research into senolytic therapies, drugs that selectively clear out aged, dysfunctional cells from tissues, has shown promising results in animal models. Scientists at institutions like the Salk Institute and the Babraham Institute in Cambridge have demonstrated partial cellular reprogramming that reverses certain markers of aging in mice. The field of longevity research has attracted serious funding from serious investors, and while dramatic life extension in humans remains far in the future, it is no longer considered a purely speculative enterprise. But even if human lifespan were extended to several centuries, an achievement that would itself represent one of the greatest medical breakthroughs in history, the journey time to any star beyond Alpha Centauri would still exceed it. And a single generation crew of long-lived humans still requires all the engineering solutions, closed-loop life support, radiation shielding, genetic maintenance that a multi-generation crew requires. The generation ship problem does not have a single solution. It has a collection of partial solutions, each of which solves some things and creates others, and the deeper you look at it, the more it resembles less of an engineering challenge and more of a civilizational one. A question not about what we can build, but about what kind of society we want to be, and what sacrifices we are willing to ask of the future in service of a dream. There is one more dimension to this that I have not yet touched on, and it is perhaps the most quietly devastating of all. When a generation ship finally arrives, after a century or 5 centuries or 1,000 years of travel, what does it find? Maybe nothing. Maybe the planet that looked promising from Earth, observed through telescopes across 4 light-years of space, turns out on closer inspection to be barren, toxic, or actively hostile to life. Remote observation from Earth, even with the best telescopes we will ever build, can only tell us so much about a world. The difference between a planet that can support life and one that cannot might come down to details invisible at interstellar distances. Atmospheric chemistry, subsurface geology, microbial ecosystems that would be lethal to humans, radiation levels at the surface, a magnetic field too weak to protect from stellar wind. And what happens to the ship's population if they arrive after 500 years of travel and find that the destination is uninhabitable? They cannot turn around and go back. They do not have the fuel. They do not have the lifespan. They do not have the Earth they left behind, which has moved on without them for 5 centuries. The philosopher Mary Midgley once wrote that we tend to evaluate the costs of great enterprises against an imagined success rather than against the full distribution of possible outcomes. A generation ship that arrives at a habitable world is a triumph of the human spirit. A generation ship that arrives at a dead rock is something else entirely, and we would not know which it was until the journey was already irreversibly complete. And yet, for all of these barriers, the engineering, the genetics, the psychology, the ethics, the uncertainty of the destination, there is something that refuses to be extinguished. Something that has driven our species from its very beginning to cross every ocean, climb every mountain, push into every hostile environment the Earth has to offer. We are explorers, not metaphorically, literally, biologically, in the structure of our curiosity and our restlessness. The same impulse that sent Polynesian navigators across the Pacific in outrigger canoes, guided by stars and wave patterns and the flight of birds. The same impulse that drove Magellan's fleet around the world, that sent Lewis and Clark into an unmapped continent, that launched Yuri Gagarin into orbit. That impulse does not calculate odds. It does not weigh ethical frameworks. It looks at the horizon, or in this case, at the sky, and it feels something that is older than language. Something that says, there, what is there? And that impulse is not a flaw. It is the engine of everything we have ever discovered. In Part 6, we are going to take a step back from the spacecraft and the star systems and look at the biggest picture of all. We are going to ask what the universe itself might be telling us about the likelihood of anyone, anywhere, making this journey, because there is a question that haunts every serious discussion of interstellar travel, a question so unsettling that one of the greatest physicists of the 20th century named it after himself over a lunch conversation. Where is everybody? If interstellar travel is possible, even difficult, even rare, then in a galaxy 13 billion years old, with hundreds of billions of star systems, at least some of which are far older than our own, someone should have done it. The math suggests the galaxy should be full of evidence of intelligent life reaching across the stars, and yet, in every direction we look, across every wavelength we can observe, the universe is silent. That silence is called the Fermi paradox, and what it implies about the barriers to interstellar travel and about our own future as a species is one of the most profound and most unsettling things in all of science. It was a casual lunch. Summer of 1950. Los Alamos National Laboratory in New Mexico, where some of the brightest minds in physics gathered daily to eat together and talk about whatever was on their minds. On this particular afternoon, the conversation had drifted toward a light-hearted topic, a New Yorker cartoon that had recently been published depicting little green aliens stealing New York City's trash cans. Someone made a joke. Laughter followed, and then Enrico Fermi, one of the architects of the first nuclear reactor, a Nobel laureate, a man whose intuition for physics was legendary among his peers, went quiet for a moment, and then, seemingly out of nowhere, he looked up from his food and asked a question that has haunted science ever since. Where is everybody? His colleagues knew immediately what he meant. If intelligent life arises naturally from the conditions of the universe, if the same chemistry and physics that produced us on this pale blue dot operates throughout a galaxy of 400 billion stars, many of them billions of years older than our Sun, then the universe should be teeming with civilizations. Some of them should be vastly more advanced than us. Some of them should have had millions of years head start on solving the problems we have been wrestling with in this video, and in that time, even at speeds far below the speed of light, a sufficiently motivated civilization could have spread across the entire Milky Way galaxy. The numbers are not subtle. Astronomers estimate there are somewhere between 100 billion and 400 billion stars in the Milky Way alone. We now know, thanks to data from the Kepler Space Telescope and its successor TESS, that planets are extraordinarily common, not the exception but the rule. Most stars have them. A significant fraction of those planets orbit within the habitable zone of their star, where liquid water could exist on the surface. The Milky Way likely contains billions of potentially habitable worlds. Given those numbers, and given the age of the galaxy, roughly 13 billion years, compared to Earth's 4.5 billion, the expectation is not just that life might exist elsewhere. The expectation, if life arises wherever conditions permit, is that the galaxy should be absolutely crowded with it, with civilizations of every age and level of development, with signals, with probes, with megastructures visible across thousands of light years, with some form of evidence detectable by a species at our technological level that others have been here or are out there or are trying to reach us, and yet, silence. Nothing. The sky is empty of signals. Our telescopes have found no megastructures. Our radio receivers have detected no coherent transmissions of artificial origin. The SETI Institute, the search for extraterrestrial intelligence, has been scanning the skies systematically for decades, using some of the most sensitive radio telescopes ever built, and has found nothing that has withstood scientific scrutiny. This discrepancy between the expectation of a galaxy full of life and the observed reality of complete cosmic silence is the Fermi paradox. And it is not just a philosophical puzzle. It is a data point, a measurement, an observation about the universe that demands an explanation. There are many proposed resolutions to the Fermi paradox, and they vary enormously in their implications. Let's walk through the most serious ones, because each of them carries a different message about the nature of interstellar travel and the future of our own civilization. The first class of solutions says the silence is not real. We simply have not looked hard enough, or in the right places, or in the right ways. Maybe alien civilizations are not communicating via radio waves, a technology that our own civilization is already moving away from in favor of tightly focused laser communications, which would be far harder to detect accidentally from light years away. Maybe the signals are there, but encoded in ways we have not yet thought to look for. Maybe the universe is full of whispers, and we have only just learned to listen, and we have been listening for only a cosmic eye blink. This resolution is comfortable. It requires no dark conclusions. It simply asks for patience and broader search strategies, and there is real merit to it. The assumption that alien civilizations would necessarily communicate in ways detectable to us is genuinely questionable. The second class of solutions acknowledges the silence, but explains it through distance and time. Perhaps interstellar travel and communication are so difficult, for exactly the reasons we have been exploring in this video, that even advanced civilizations simply cannot bridge the gaps between stars in any detectable way. The barriers we have been discussing are not uniquely human problems. They are universal. They apply to any civilization made of matter, operating under the same laws of physics that govern us. Perhaps the silence tells us not that we are alone, but that the universe's rules make genuine interstellar community effectively impossible for anyone. This explanation carries a strange comfort. It suggests we are not special in our isolation. Every civilization in the galaxy sits on its island, looking out at the dark water between the stars, and faces exactly the same walls we face. But then there is a third class of solutions, and these are the ones that physicists and astrobiologists discuss in quieter tones, because their implications are, depending on your temperament, either deeply sobering or genuinely terrifying. They go under the collective name of the Great Filter. The idea was developed most influentially by economist and futurist Robin Hanson in 1998. The argument goes like this. Given the age and size of the galaxy and the apparent rarity of detectable civilizations, something must be filtering out the development of spacefaring civilizations before they become visible across cosmic distances. Some step or series of steps in the progression from simple chemistry to interstellar civilization is extraordinarily rare enough to explain the silence. The crucial question, and this is where the idea becomes genuinely haunting, is whether that filter lies behind us or ahead of us. If the filter is behind us, that is, if the extraordinarily improbable step is something in our past, the origin of life itself, the emergence of complex multicellular organisms, the development of human-level intelligence, then we may have already passed through the bottleneck. We may be among the rare ones, the lucky ones. The galaxy may be littered with worlds where life began and stalled, where evolution never produced anything beyond microbes, where intelligence flickered and went dark before it ever looked up at the stars. And we made it through. That would be an extraordinary thing to contemplate. Our existence would be among the most improbable events in the history of the universe, and the silence would be explained not by catastrophe ahead of us, but by extraordinary fortune behind us. But if the filter lies ahead of us, If the rare and terrible thing is something that civilizations at our level of development typically encounter and do not survive, then the silence carries a very different message. It means that civilizations that develop technology comparable to ours almost universally fail to become interstellar. They hit something they cannot overcome, and then they go quiet. What could that something be? The possibilities range from the mundane to the cosmic, self-destruction through nuclear war or engineered pathogens or environmental collapse. The development of artificial intelligence that supersedes and replaces biological intelligence in ways that are not compatible with long-term civilizational survival. Some unknown physical barrier that destroys civilizations at a specific technological threshold, or perhaps something stranger, something we have not yet imagined because we have not yet encountered it. Here is the thing that makes the Great Filter genuinely useful as a lens for thinking about interstellar travel. It reframes the question. Instead of asking, why is interstellar travel so hard for us specifically, it asks, why is the transition from planetary civilization to interstellar civilization apparently so rare across the entire galaxy? And one of the most plausible answers is sitting right in the middle of everything we have discussed over the last 5 parts of this video. The barriers to interstellar travel are not engineering problems that any sufficiently advanced civilization will inevitably solve. They may be fundamental. They may be rooted in the deepest laws of physics in ways that no amount of technological progress can circumvent. The speed of light may be genuinely unbreakable. Exotic matter may genuinely not exist in usable form. The energy requirements may genuinely be prohibitive for any civilization operating within known physics. If that is true, then the Great Filter might not be a catastrophe. It might simply be physics. The universe may be structured in such a way that civilizations are effectively contained on their homeworlds, or at most within their home star systems, forever. Not by violence or bad luck or bad decisions, but by the architecture of space-time itself. That is simultaneously one of the most humbling and one of the most thought-provoking conclusions you can draw from the Fermi paradox, because it suggests that intelligence might be far more common in the universe than we think, that the galaxy might be full of civilizations, each one brilliant and complex, and perhaps profoundly different from us, but that they are separated from each other by distances so vast and barriers so fundamental that contact between them is in practice impossible. A universe of islands, each one inhabited, none of them able to reach the others. There is a specific version of the Great Filter that I want to spend a moment on, because it has gained significant traction among astrobiologists in recent years, and because it connects directly to the question of where we stand as a civilization right now. It is sometimes called the rare Earth hypothesis, though it has evolved considerably from the original formulation by geologist Peter Ward and astronomer Joe Brownlee in their 2000 book of the same name. The basic argument is that the conditions required for the emergence of complex, intelligent life are far more specific and far more rare than the simple habitable zone calculations suggest. It is not enough for a planet to be at the right distance from its star to have liquid water. The star itself needs to be the right kind, not too massive, which means too short-lived, not too active, which means too much radiation, not a binary or multiple star system, which can create gravitational instabilities in planetary orbits. The planet needs a large moon, which stabilizes its axial tilt and prevents the kind of extreme climate swings that might prevent complex life from gaining a foothold. It needs plate tectonics, which cycles carbon through the atmosphere and maintains a long-term climate thermostat. It needs a Jupiter-sized planet in its outer solar system, which acts as a gravitational shield, deflecting or capturing the comets and asteroids that would otherwise bombard the inner system with catastrophic frequency. Earth has all of these things. And the probability that any given planet has all of these things simultaneously in the right proportions for the right duration, that probability might be extraordinarily low. If rare Earth is correct, then even in a galaxy of hundreds of billions of stars, truly Earth-like worlds capable of producing not just life but complex, intelligent, technological life, might be vanishingly rare, perhaps dozens, perhaps fewer, spread across a galaxy 100,000 light-years in diameter, so far apart from each other that even the radio signals they emit take tens of thousands of years to cross the distance between them. In that picture, interstellar communication is not just difficult. It may be practically futile. By the time a signal from a distant civilization reaches us, that civilization may have been extinct for longer than our entire species has existed. Now, I want to be careful here, because the rare Earth hypothesis is not without its critics, and the history of science is littered with arguments that claimed life or intelligence was special and rare, only to be overturned by new discoveries. Before the Kepler Space Telescope, some astronomers seriously argued that planetary systems like ours might be uncommon. Kepler destroyed that idea decisively. Before the discovery of extremophiles, organisms that thrive in conditions once considered absolutely hostile to life, in boiling acidic hot springs, in the crushing darkness of deep ocean vents, in the frozen deserts of Antarctica, the range of environments considered potentially habitable was far narrower than we now know it to be. Before we understood that liquid water exists beneath the ice of Europa and Enceladus and possibly Ganymede, the idea that life might exist within our own solar system beyond Earth seemed remote. Every time we have assumed that life requires exactly the conditions we enjoy on Earth, the universe has surprised us, and that pattern of surprise is worth taking seriously. The astrobiologist David Grinspoon makes a point that I find deeply compelling. He argues that we are still in the very earliest moments of our search for life beyond Earth. We have been searching seriously for extraterrestrial signals for about 60 years. We have directly sampled the surface of one other planet, Mars, in any detail. We have barely begun to characterize the atmospheres of exoplanets. To conclude from this early, limited search that life is rare would be like an explorer standing on the beach of a new continent after an hour of walking and concluding there are no cities here. We have not been looking long enough or carefully enough or in enough places to draw confident conclusions about the frequency of life in the universe. The silence of the cosmos is data, but it is not yet enough data to tell us the whole story. What the Fermi paradox does tell us with reasonable confidence is that interstellar civilizations, if they exist, are not obvious. They are not filling the galaxy with signals and megastructures and evidence of their presence in ways that our current instruments would detect. Whether that is because they are rare, or because the barriers to interstellar expansion are universal, or because civilizations tend not to survive long enough to become truly interstellar, any of those explanations point toward the same practical conclusion. The stars are not easy to reach. For anyone, for anything made of matter, operating under the physics of this universe, the stars maintain a distance that resists every approach we can currently imagine. And there is something in that. Something that, if you let yourself really feel it, is both devastating and beautiful. We are here, on this small, warm, improbably alive planet, wrapped in an atmosphere thin enough that you can drive to its edge in an hour, orbiting a star that is one of 400 billion in our galaxy, which is one of perhaps 2 trillion galaxies in the observable universe. And we know it. We know where we are. We know how we got here. We know the age of the universe and the mass of the electron and the expansion rate of the cosmos and the composition of stars 4 billion light-years away. We know these things because we are curious, because we built telescopes and particle accelerators and gravitational wave detectors and sent probes to the edges of our solar system, because we refused to be satisfied with not knowing. And that same refusal, that same stubborn, beautiful, deeply human insistence on understanding is exactly what will determine what happens next. Because in Part 7, we are going to talk about something that I think is the most genuinely hopeful part of this entire conversation. Not hopeful in a naive or wishful way. Hopeful in the way that the history of science earns the right to be hopeful. We are going to look at what is actually happening right now. The real missions, the real experiments, the real breakthroughs at the frontier of physics and propulsion research that are slowly, carefully, methodically chipping away at the barriers we have been describing. Because every wall, no matter how thick, has a story about how it was built. And if you understand how it was built, you begin to understand where the weaknesses are. The universe has not given us a map, but it has left us clues. And some of the most brilliant people alive today are following them. There is a particular kind of scientist that I find endlessly fascinating. Not the ones who work comfortably within established frameworks, publishing incremental results in well-trodden fields. The ones I find most compelling are the ones who choose to work at the edge. The ones who look at a problem that most of their colleagues consider either solved or unsolvable and decide that neither conclusion is good enough. The ones who get up every morning and go to work on something that might not pay off in their lifetime or their children's lifetime, but that matters so profoundly that they cannot imagine doing anything else. Right now, scattered across universities and research institutes and government laboratories and private companies on every inhabited continent, there are people doing exactly that. Working on the problem of going to the stars, not as a hobby, not as a thought experiment, as a vocation, with real funding, real equipment, real mathematics, and a real understanding of how difficult the challenge is. And some of what they are finding is genuinely extraordinary. Let's start with propulsion, because that is the most fundamental barrier and the one attracting the most serious research attention right now. We talked in Part 2 about the Breakthrough Starshot Initiative, the laser sail concept aimed at sending gram-scale probes to Alpha Centauri at 20% of the speed of light. That program is not stalled. It is actively progressing. Researchers at the University of California, Santa Barbara, funded through the Breakthrough Starshot program, have been working on the laser array technology needed to accelerate the tiny spacecraft. The challenge of phase-locking thousands of individual lasers into a single coherent beam, keeping them all perfectly synchronized so their light adds together constructively rather than destructively, is one of the hardest engineering problems in photonics, but progress is being made. Published results from 2022 showed kilometer-scale coherent beam combining was closer to practical implementation than many had expected. The sail material itself is another active frontier. The sail needs to be extraordinarily thin. We are talking about layers just nanometers thick to minimize mass. It needs to reflect the laser light with near-perfect efficiency, because any absorbed energy becomes heat that would instantly vaporize the sail. And it needs to survive the brutal radiation environment of interstellar space for 2 decades. Researchers are exploring materials like silicon nitride and photonic crystal structures that can achieve the necessary combination of reflectivity, thinness, and durability. None of these materials exist in production-ready form yet, but the science is advancing. What makes Breakthrough Starshot particularly interesting from a philosophical standpoint is that it is not trying to send humans, it is trying to send sensors, cameras, basic instruments that could image a planet orbiting Proxima Centauri and transmit data back to Earth. The images would not arrive for over 4 years after transmission, the time it takes light to cross that distance, but they would be real. Direct observations of another star system, the first in human history. That alone would be worth the effort. That alone would change something fundamental about how our species sees itself in the cosmos. On the nuclear propulsion front, NASA has been quietly but seriously investing in a concept called nuclear thermal propulsion, or NTP. This is distinct from the nuclear pulse propulsion of Project Orion. Instead of detonating bombs, a nuclear thermal rocket uses a nuclear reactor to heat a propellant, typically liquid hydrogen, to extremely high temperatures and then expels it through a nozzle to generate thrust. The exhaust velocity achievable with nuclear thermal propulsion is roughly twice that of the best chemical rockets, which translates directly into significantly better fuel efficiency. NASA and DARPA, the Defense Advanced Research Projects Agency, announced a joint program in 2023 called DRACO for demonstration rocket for agile cislunar operations, aimed at demonstrating nuclear thermal propulsion in space by the mid-2020s. This is not an interstellar drive. It is designed for faster travel within our solar system, reaching Mars in potentially as little as 4 months, rather than the 7 to 9 months required by current chemical propulsion systems. But it is a critical stepping stone, proving nuclear propulsion in space, understanding its operational characteristics, building the engineering knowledge base. All of that is foundational work that points in the direction of something faster. Further along the theoretical spectrum, a concept called the nuclear photonic rocket proposes using the energy from nuclear reactions not to heat a propellant, but to generate intense beams of photons, light, which are then expelled from the spacecraft. Because photons travel at the speed of light, the exhaust velocity of a photonic rocket is the maximum physically possible. The efficiency is extraordinary in theory. The thrust, unfortunately, is extremely low for a given power output, meaning you need truly enormous amounts of nuclear energy to produce meaningful acceleration. The mass of the reactor required makes this impractical with current technology, but as nuclear engineering advances and miniaturization continues, some researchers believe photonic propulsion could eventually achieve velocities of a few % of the speed of light. Then there is antimatter propulsion, and this one sits in a category of its own because the physics is unimpeachable. Antimatter is not a theoretical construct, it is real, it has been produced in laboratories, and its properties are exactly as predicted by quantum field theory. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass into energy. No other energy source even comes close to that efficiency. Nuclear fission converts less than 1% of mass into energy. Nuclear fusion does somewhat better, but still only a few %. Antimatter annihilation is the theoretical ceiling, the most energy you can extract from a given mass, by the laws of physics as we understand them. A spacecraft propelled by matter-antimatter annihilation could theoretically achieve velocities approaching a significant fraction of the speed of light. The exhaust from an antimatter drive, the products of proton-antiproton annihilation, are high-energy pions, which can in principle be directed by magnetic fields to produce thrust. Studies conducted at Pennsylvania State University and the Tau Zero Foundation, among others, have shown that an antimatter rocket could theoretically reach Proxima Centauri in somewhere between 40 and 100 years, depending on the specific design parameters. The problem, and it is an enormous problem, is production. Antimatter is produced in particle accelerators like CERN's Large Hadron Collider as a byproduct of high-energy collisions. The total amount of antimatter produced by all the particle accelerators in human history combined is estimated to be around 15 nanograms, 15 billionths of a gram. At current production rates and energy costs, producing a single gram of antimatter would cost something in the range of $62 trillion and take longer than the current age of the universe. A viable antimatter rocket would require kilograms, not nanograms. The gap between what we produce and what we would need is not a gap that better engineering alone can close. It requires either a fundamental breakthrough in the efficiency of antimatter production, which would require new physics, or the discovery of naturally occurring concentrations of antimatter somewhere in the cosmos, which current observations suggest do not exist in accessible quantities. Antimatter propulsion is real physics attached to an impossible supply chain, at least for now. But here is where things get genuinely interesting, in a way that I think does not get enough attention outside specialist circles. In the past decade, our understanding of the quantum vacuum, the lowest energy state of space itself, has evolved in ways that have surprised even the physicists working in the field. The quantum vacuum is not nothing. It is a seething, dynamic medium filled with quantum fluctuations, virtual particle pairs constantly blinking in and out of existence, fields with non-zero energy even in the complete absence of matter. The Casimir effect, which we mentioned briefly in Part 3, is a measurable, experimentally confirmed consequence of these vacuum fluctuations. A tiny but real attractive force between two closely spaced metal plates, caused by the difference in vacuum energy between the inside and outside of the gap. Some researchers are exploring whether the quantum vacuum might be manipulated in ways that produce useful effects for propulsion. The ideas are highly speculative, and most mainstream physicists treat them with significant skepticism. But the fact that the quantum vacuum has real, measurable physical effects that were themselves considered speculative before they were confirmed, means that serious physicists are reluctant to simply dismiss the possibility entirely. Harold White, whom we mentioned in connection with the Alcubierre drive research, has been working at the interface of quantum vacuum physics and propulsion concepts for years, first at NASA and more recently through his own research organization. In 2021, a team he was involved with announced the detection of what they described as a potential warp bubble structure at the nanoscale, an observation they made while studying Casimir cavities. The announcement generated significant media attention and significant scientific debate. Most physicists expressed deep skepticism about whether the observed structure was actually related to warp physics in any meaningful sense. The paper underwent revision and the claims were substantially walked back. But the broader research direction, understanding the quantum vacuum, probing its properties, looking for effects that current theory does not fully predict, is not fringe science. It is careful, methodical work at a genuine frontier. And frontiers, by definition, are places where the map runs out and the unexpected becomes possible. There is another frontier that I think carries even more near-term promise, not for interstellar travel directly, but for the foundational science that interstellar travel will ultimately require, and that is our rapidly deepening understanding of space-time itself. General relativity describes gravity as the curvature of space-time caused by mass and energy. It is the most precisely tested theory in the history of physics, and yet we know it is incomplete. At the scales where quantum mechanics becomes important, inside black holes at the moment of the Big Bang, general relativity produces mathematical infinities, which is physics's way of saying something is missing from this picture. The effort to complete that picture, to build a theory of quantum gravity that works at all scales, is generating insights that no one fully anticipated. Loop quantum gravity, one of the leading approaches, suggests that spacetime itself is not continuous but discrete, that there is a smallest possible length, called the Planck length, at roughly 1.6 times 10 to the negative 35 meters, below which the concept of distance loses its meaning. If space-time is fundamentally granular rather than smooth, that changes the nature of the speed limit in ways that physicists are still working through. String theory, the other major approach, suggests that the particles and forces we observe are manifestations of tiny vibrating strings of energy existing in more than the 4 dimensions we experience, potentially 10 or 11 dimensions in total. The extra dimensions are compactified, curled up at scales far too small to detect directly. But some versions of string theory predict that certain conditions could temporarily or locally alter the effective properties of space-time in ways that might, in principle, allow for effects resembling faster-than-light travel. I want to be honest with you about what this means. These are not engineering blueprints. They are not even confirmed physical theories. Both loop quantum gravity and string theory are works in progress, and neither has yet made a clear, unambiguous prediction that has been confirmed by experiment in a way that definitively validates the theory over competitors. They are the most serious attempts we have at the next level of understanding, and they may be completely right, partially right, or eventually superseded by something better, but the trajectory is clear. Our understanding of space-time is deepening. The questions we can ask are becoming more precise. The instruments we are building, upgraded gravitational wave detectors, next-generation space telescopes, more powerful particle colliders, are probing reality at scales and energies never before accessible. And every time we have probed reality at a new frontier in the history of physics, we have found something that rewrote the textbooks. There is one more research direction I want to highlight, because it is perhaps the most imaginative and the most genuinely mind-expanding idea currently being seriously explored in the context of interstellar travel. And it comes not from propulsion physics or space-time geometry, but from information theory and the science of life itself. We talked in Part 4 about the idea of sending information rather than matter across interstellar distances. But some researchers are taking this idea further, much further, into territory that sounds like science fiction but is grounded in real biology and real information theory. The concept goes by various names, but one of the most discussed is interstellar panspermia by design, not the accidental transfer of microbial life between planets via asteroid impacts, which is a real, scientifically plausible process called lithopanspermia, but the deliberate encoding and transmission of biological information across interstellar distances. Here is the core idea. Life, at its most fundamental level, is information. The DNA in every cell of your body is a molecular data storage system, encoding the instructions for building and operating a living organism in a chemical language of 4 bases: adenine, thymine, guanine, and cytosine. The human genome contains roughly 3 billion base pairs. In digital terms, that is about 750 megabytes of information. 750 megabytes is trivial to transmit as a radio signal, even at interstellar distances. A powerful enough transmitter could beam that information to another star system in the time it takes light to travel there. Nothing can do it faster, but light can certainly carry the data. Now, what would you do with that information when you received it? If you had the technology to synthesize DNA from a transmitted sequence, and the technology to insert that DNA into an appropriate cellular chassis, and the technology to develop the resulting embryo, you could, in principle, reconstruct the biological blueprint of the organism that sent the signal. This concept, sometimes called directed panspermia or seeding by signal, was explored by the Nobel Prize-winning biologist Francis Crick, one of the co-discoverers of the double helix structure of DNA, as early as 1973. He proposed that life on Earth might itself have been seeded deliberately by an advanced extraterrestrial civilization. Most astrobiologists consider this unnecessary as an explanation for Earth's life, but as a strategy for interstellar propagation, as a way for a civilization to spread its biology across the galaxy at the speed of light. It is a genuinely fascinating concept. The ethical dimensions are, again, extraordinary. Transmitting the blueprint of a human being or of all life on Earth to an unknown receiver in an unknown civilization raises questions about consent, about identity, about what it means to be a person, that make even the generation ship ethics we discussed in Part 5 look straightforward. But the physics works. That is the remarkable thing. The physics of transmitting biological information across interstellar distances works entirely within known science. No exotic matter required, no violation of the speed limit, just information, riding light, crossing the void. What strikes me most about all of these research directions: laser sails, nuclear propulsion, antimatter, quantum vacuum physics, quantum gravity, biological information transmission, is not any individual idea. It is the pattern, the sheer diversity and creativity of the approaches that serious, credentialed, careful scientists are bringing to this problem. Human beings are extraordinarily good at something that no other species on this planet has ever demonstrated. We are good at collaborative, cumulative, multi-generational problem solving. We build on each other's work across centuries. Newton famously said he stood on the shoulders of giants, and the giants he was referring to had been dead for 1,000 years. The knowledge accumulated by our ancestors is the foundation we stand on. The knowledge we generate today is the foundation our descendants will stand on. And here is what that means for interstellar travel. The barriers we have described in this video are real. They are not going away. The speed of light is not going to increase. The rocket equation is not going to become more forgiving. The distances between stars are not going to shrink, but our understanding of the universe is going to deepen. It always has. And when that understanding reaches the level where the next great revolution in physics becomes possible, and there will be a next revolution because our current theories are demonstrably incomplete, the landscape of what is possible will change in ways we cannot currently predict. That is not wishful thinking. That is the most consistent pattern in the entire history of human knowledge. And there is something else worth saying here. Something that tends to get lost in the enormity of the technical challenges. Even if we never send a human being to another star, even if the barriers turn out to be genuinely permanent, grounded in physics that no revolution will overturn, even if the generation ship is never built, the antimatter never produced, the warp geometry never realized, the act of trying has value that is independent of the outcome. The technologies developed in pursuit of interstellar travel have already changed life on Earth in ways most people do not realize. Solar panels, water purification systems, scratch-resistant lenses, memory foam, the cameras in your phone, GPS, the internet itself, all of these have roots in the space program. The pursuit of the impossible has a remarkable habit of producing the merely very difficult as a byproduct. And more than the technology, the perspective, there is something that happens to human beings when they genuinely grapple with the scale of the cosmos, when they really sit with the distances, the timescales, the number of worlds out there, the age of the universe. Something shifts. The things that divide us, the borders, the arguments, the anxieties of daily life, begin to look different against the backdrop of 400 billion stars, not unimportant, but differently proportioned. Carl Sagan called this the overview effect at a civilizational scale, the same shift in perspective that astronauts describe when they see Earth from orbit, that sudden, visceral understanding that we are all on the same small vessel, that the borders are invisible from above, that we are one species on one world in an incomprehensibly vast cosmos. That shift is available to all of us if we are willing to look up. In Part 8, we are going to take that perspective and apply it to something deeply personal. We are going to talk about what all of this means for us, not as a civilization, not as a species, but as individual human beings alive right now at this specific and remarkable moment in cosmic history. Because there is a question underneath all of this that I have been building towards since the very beginning of this video. And it is not a physics question, it is a question about meaning, about what it means to be aware of your own smallness and to find in that smallness not despair, but something closer to its opposite. And along the way, we are going to talk about something that I think is one of the most beautiful and most underappreciated facts in all of science. Something about what you are made of and where it came from, and what that tells you about your relationship to the stars you can never reach. Stay with me. If you are still watching, don't forget to subscribe to the channel and hit the thumbs up. You will be part of a community that explores the cosmos together. Let me tell you something about the iron in your blood. Every single atom of it was forged inside a star, not metaphorically, not poetically, literally, physically, in the nuclear furnace at the core of a massive star that lived and died before our sun was born. The iron in your hemoglobin, the iron that right now is carrying oxygen through your body, keeping you alive, making this moment possible, was synthesized in a stellar core under pressures and temperatures so extreme that the numbers lose their meaning to everyday experience. Hundreds of millions of degrees, densities millions of times greater than anything on Earth's surface. And when that star reached the end of its life, when the nuclear fuel ran out and the outward pressure of fusion could no longer hold back the inward crush of gravity, it exploded, a supernova, one of the most violent events in the known universe, briefly outshining entire galaxies, releasing more energy in a few seconds than our sun will emit across its entire 10 billion year lifespan. And in that explosion, the iron and carbon and oxygen and nitrogen and every other element heavier than hydrogen and helium were scattered across light years of space, seeding the surrounding gas clouds with the raw materials of future worlds. Some of that scattered material drifted through the galaxy for hundreds of millions of years. Eventually, drawn together by gravity, it began to collapse into a new solar system, a new star ignited at the center. Around it, the remaining material clumped and collided and built itself into planets. One of those planets, the third from the new star, developed liquid water on its surface, and in that water, over billions of years, chemistry became biology, biology became complexity, complexity became consciousness, and here you are, reading, thinking, wondering, made of the ash of dead stars, animated by a process so improbable and so ancient that the mind genuinely struggles to hold it. You are not separate from the cosmos. You are the cosmos, looking at itself. The physicist Richard Feynman once said that if you want to understand nature, you have to be comfortable with the idea that it is strange, really strange. Not strange in the way a magic trick is strange, where the strangeness dissolves once you know the secret, but strange in a way that deepens the more carefully you look. The universe is not obligated to make sense to human intuition. It is only obligated to be what it is, and what it is extraordinary. Consider the timescales alone. The universe is approximately 13.8 billion years old. Our sun formed about 4.6 billion years ago. Life appeared on Earth roughly 3.5 to 4 billion years ago, within a few hundred million years of the planet's formation, which is fascinatingly fast by cosmic standards. Complex multicellular life did not appear until about 600 million years ago. Our genus, Homo, emerged perhaps 2 to 3 million years ago. Anatomically modern humans have existed for somewhere around 300,000 years. Written language is perhaps 5,000 years old. Modern science, the systematic, mathematical, experimental investigation of nature, is roughly 400 years old. 400 years. Out of 13.8 billion, we are infants. Cosmically speaking, we have barely opened our eyes. The questions we are wrestling with in this video: can we reach the stars? Are we alone? What is the universe made of? Are questions we have been capable of even asking in their current, precise, scientific form for only the tiniest sliver of cosmic time. And in that sliver, look at what we have figured out. We mapped the structure of space-time. We split the atom. We decoded the genome. We detected ripples in the fabric of reality from collisions that happened a billion light-years away. We photographed a black hole. We landed robots on Mars and flew a helicopter in its thin atmosphere. We found planets orbiting other stars, thousands of them. We traced the history of the universe back to its first fractions of a second. This is not a species that is done. This is a species that is just getting started, and yet there is something important in sitting honestly with the limits, not as a defeat but as a teaching. The barriers to interstellar travel, every single one of them that we have walked through together over the course of this video, are not signs that the universe is hostile to us. They are signs that the universe is vast, incomprehensibly, breathtakingly, almost insultingly vast, and there is a difference between those two things that matters enormously for how you carry this knowledge. A hostile universe would be one designed to frustrate us, one where the laws of physics seem specifically calibrated to keep us in our place, to mock our ambitions, to ensure that our reach always exceeds our grasp. And it is possible to look at the speed of light and the rocket equation and the distances between stars and feel something like that, something like being locked in a room. But I think that reading misses something essential, because the same laws of physics that impose the speed of light also make chemistry possible. They make stars possible. They make planets possible. They make DNA possible. They make you possible. The constants of nature, the strength of the electromagnetic force, the mass of the electron, the value of the cosmological constant, are calibrated with almost eerie precision to permit the existence of complexity, of matter, of life. Change any of them by even a small fraction, and stars do not form, or atoms do not bond, or the universe collapses back on itself before anything interesting can happen. We live in a universe that permits us to exist, that permits us to be curious, that permits us to look up and ask where those points of light are and whether we can reach them. Whether or not we ever physically cross the distance to another star, that permission, that extraordinary, improbable, unrepeated gift is worth something. The cosmologist Sean Carroll has written about what he calls poetic naturalism. The idea that a universe without supernatural meaning is not therefore a universe without meaning. That meaning is something minds create, not something the universe provides pre-packaged. And the meaning that a curious, aware, connected mind can create from an honest understanding of the cosmos is, he argues, richer than any alternative, because it is real, because it is earned, because it requires you to actually look at the universe as it is, not as you wish it were, and find something worth loving in what you see. I find that deeply compelling, not as a consolation prize for the absence of easy interstellar travel, but as a genuine and hard-won perspective. Let me tell you about a photograph. You may have seen it before, but I want to describe it carefully because it deserves more than a passing glance. On February 14, 1990, as Voyager 1 was leaving our solar system, the spacecraft was commanded to turn its camera back toward the inner solar system and take a series of photographs. The result was what Carl Sagan called the pale blue dot, an image of Earth from a distance of roughly 6 billion kilometers. In the photograph, our planet appears as a tiny point of light, less than a single pixel across, suspended in a beam of scattered sunlight against the absolute blackness of deep space. Sagan wrote about that image in a way that I think deserves to be read slowly. He wrote that every human being who ever lived, every king and peasant, every young couple in love, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. He wrote that the Earth is a very small stage in a vast cosmic arena, that our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale blue light. And he concluded, and this is the part I come back to again and again, that there is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To him, it underscored our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. That image was taken from a spacecraft moving at 17 kilometers per second, the one that, at that speed, would take 73,000 years to reach the nearest star, the one that carries a golden record with the sounds of Earth encoded on it, drifting now through interstellar space, an ambassador from a species that looked up at the night sky and decided that the universe deserved to know they were here. There is a concept in astronomy called the cosmic perspective. It is not a formal scientific term. It is more of a stance, a way of orienting yourself relative to the information that science provides. Neil deGrasse Tyson, who has written beautifully about this, describes it as a view of the world that is simultaneously humbling and empowering. Humbling because it confronts you with your own smallness. Empowering because it reveals that you are part of something so much larger than yourself that the distinction between self and cosmos begins to blur at the edges. The cosmic perspective does not make your problems go away. It does not make grief smaller or injustice more tolerable or loneliness less sharp. What it does, what I have found it does, and what I hear again and again from people who genuinely engage with this material, is change the texture of those experiences. Add a dimension to them, place them in a context so vast that they become, paradoxically, both more significant and less overwhelming, because here is the thing, you are made of atoms that have existed for nearly 14 billion years. The hydrogen in your body was forged in the first 3 minutes after the Big Bang. The heavier elements were forged in stars across billions of years of cosmic history. You are not a visitor to the universe. You are not an observer looking in from outside. You are a local expression of the universe's ongoing process of complexification. You are what the universe does when it has had 13.8 billion years to practice, and the fact that you are sitting here, right now, aware of all of this, aware of the distances and the barriers and the silence and the age and the scale, that awareness is itself one of the rarest and most astonishing things we have ever found in the cosmos. Because as far as we know, and our search has been genuinely earnest if still limited, the universe has produced awareness in only one place that we can confirm. Here, on this pale blue dot, in you. That does not mean we are alone. I want to be careful not to overstate what the silence tells us as we discussed in part 6. But it does mean that whatever awareness is, whatever this phenomenon of experience and curiosity and wonder actually is, at its deepest level, it is rare enough and precious enough that its existence on this one world is not something to be taken lightly. And when I think about the barriers to interstellar travel, all of them, stacked together, immovable and fundamental and enormous, what I feel is not despair. What I feel is something closer to reverence, because those barriers are what make this moment matter. If we could hop between stars the way we hop between cities, the universe would be smaller, not in physical size but in meaning. The distance between the stars is what makes looking up at them an act of longing rather than just navigation. The impossibility of reaching them easily is what makes reaching toward them an expression of something fundamental about what we are. We are the species that looks at things it cannot have and decides to understand them anyway. That maps the territory it cannot enter. That sends golden records into the void not because anyone is likely to find them, but because sending them says something true about who we are. But here is something I have not yet said directly. Something that feels important to say before we move into the final sections of this video. The barriers to interstellar travel are real, but they are barriers as understood by the physics we know today, and our physics today is incomplete. We know it is incomplete. We have a detailed map of its incompleteness, which is itself a remarkable thing. We know exactly where the edges of our understanding are. We know precisely which questions we cannot yet answer, and why, and what answering them would require. That is not a small thing. In the entire history of our species, across hundreds of thousands of years of human existence, we have only had the tools to ask these questions at this level of precision for a few decades. The first gravitational wave was detected in 2015. The first image of a black hole was captured in 2019. The first confirmed detection of an exoplanet atmosphere with biosignature candidates from the James Webb Space Telescope came in 2023. These are not old discoveries. They are happening right now within the memory of people alive today. We are at the very beginning of reading the universe's deepest text, and the chapters we have not yet reached may contain things that change everything. I want to share something personal here. Something that I think is true for a lot of people who spend time seriously engaging with this material. There are moments, looking up at a clear sky, or reading about the first image of a black hole, or learning about the James Webb Telescope finding complex organic molecules in the atmosphere of a distant exoplanet, when the scale of all of this stops being abstract and becomes visceral, when the universe stops being a topic and starts being an experience, when the distance to the nearest star stops being a number and starts being a feeling. And in those moments, the question is not whether we can go there. The question is what it means that we even want to. What it says about us that we look at something so impossibly far away and feel not just curiosity, but something that resembles longing, something that resembles love. Because you do not long for things that do not matter. You do not feel the pull of the stars if the stars are not, in some deep and real way, part of you. And they are. Every atom in your body traces its origin to the same process that built those stars. Every pattern of chemistry that makes you alive was written in the same physical laws that govern their nuclear fires. The distance between you and the nearest star is not the distance between a person and a foreign thing. It is the distance between one part of the universe and another. We are not trying to reach something alien. We are trying to come home to something vast. In Part 9, we are going to bring all of this together. We are going to look at the practical reality of what our civilization is actually building right now. The telescopes, the missions, the technologies that are extending our reach, even if our bodies cannot follow. And we are going to ask, honestly and carefully, what the next 100 years might look like for humanity's relationship with the cosmos. Because the story of interstellar travel is not over, it has barely begun. And the next chapter is being written right now by real people with real instruments and real curiosity on a pale blue dot in the outer arm of an ordinary galaxy in the vast, silent, extraordinary universe. Right now, at this exact moment while you are watching this video, something remarkable is happening roughly 1.5 million kilometers from Earth. Orbiting a gravitational equilibrium point called the second Lagrange point, a location where the gravitational pulls of the Earth and Sun balance perfectly, allowing an object to orbit in sync with our planet. The James Webb Space Telescope is doing something that would have seemed like pure fantasy to astronomers just a generation ago. It is looking at starlight that passed through the atmosphere of a planet orbiting another star. And in that starlight, encoded in the specific wavelengths of light that were absorbed on the way through, it is reading the chemical composition of an alien sky. This is not a metaphor. This is not an approximation. This is direct, quantifiable, peer-reviewed science. The Webb telescope has already detected carbon dioxide, water vapor, methane, sulfur dioxide, and, in a result that sent a quiet tremor through the astrobiology community, dimethyl sulfide in the atmospheres of exoplanets. Dimethyl sulfide is particularly interesting because on Earth it is produced almost exclusively by living organisms, specifically by marine phytoplankton. Its detection in an exoplanet atmosphere does not confirm life. There may be abiotic processes that produce it in certain planetary conditions, and the scientific community is appropriately cautious, but it is the kind of signal that a generation ago we had no instrument capable of detecting at all. Webb is not just finding molecules. It is finding questions that are so precise, so specific, so scientifically tractable, that answering them feels, for the first time in history, genuinely within reach. Not in centuries, in decades. Let's map out what is actually being built and launched and planned across the next several decades, because the picture, when you look at it whole, is one of the most extraordinary expansions of human sensory reach in the history of our species. On the ground, a new generation of telescopes is either under construction or in advanced planning that will dwarf anything currently operating. The extremely large telescope, being built by the European Southern Observatory on a mountain called Cerro Armazones in the Atacama Desert of Chile, will have a primary mirror 39 meters across, nearly 4 times the diameter of the largest existing optical telescopes. Its light collecting area will be so enormous that it will be able to directly image Earth-sized planets orbiting nearby stars and analyze their atmospheres in detail that current instruments cannot approach. First light is currently expected sometime in the late 2020s. The 30-meter telescope, planned for Mauna Kea in Hawaii, a project that has faced significant and legitimate cultural and environmental opposition from native Hawaiian communities, a dimension of this story that deserves acknowledgement and respect, would, if completed, provide similar capabilities from the Northern Hemisphere. The giant Magellan telescope, under construction in Chile's Las Campanas Observatory, will add its own extraordinary light-gathering power to the global network. Together, these instruments will give humanity eyes sharp enough to study the surfaces and atmospheres of nearby exoplanets in a level of detail that could, in principle, reveal not just the presence of potentially life-related chemistry, but actual seasonal variations, weather patterns, and large-scale surface changes consistent with biological activity. We will not be landing on those planets. We will not be sending probes there in any time frame that matters to anyone alive today. But we will be able to study them with a richness and depth that transforms them from points of light into worlds. That transformation matters. It is not interstellar travel, but it is interstellar knowing. And knowing, as every scientist and every curious human being understands intuitively, is its own form of arrival. In our space, the planned successory missions to Webb are equally extraordinary. NASA's Habitable Worlds Observatory, the flagship mission recommended by the 2021 Decadal Survey on Astronomy and Astrophysics, the document that sets priorities for American space science for the following decade, is designed specifically to search for biosignatures on Earth-like planets in the habitable zones of nearby stars. It will be a large space telescope operating in ultraviolet, optical, and infrared wavelengths, designed to directly image and spectroscopically analyze the atmospheres of dozens of potentially habitable worlds. The mission is still in its formative stages. Launch is currently envisioned for some time in the late 2030s or early 2040s. But its scientific objectives are unambiguous and its technology roadmap is being actively developed. It represents the moment when the search for life beyond Earth transitions from a background scientific activity, something done on the side with instruments not specifically designed for it, to the primary, explicit, funded objective of a flagship space mission. Think about what that means. Within the lifetime of most people watching this video, we may have a dedicated space telescope whose entire purpose is to look at nearby Earth-like worlds and determine whether their atmospheres carry the chemical signatures of life. We may have an answer, or at least a much more informed estimate, to one of the oldest and most profound questions our species has ever asked. Are we alone? On the solar system exploration front, the missions currently in development are extending our reach in ways that directly inform the interstellar question. The Europa Clipper spacecraft, launched by NASA in October of 2024, is on its way to Jupiter's moon Europa, an ice-covered world with a global subsurface ocean of liquid water heated by tidal forces from Jupiter's immense gravity. The ocean beneath Europa's ice shell is estimated to contain roughly twice the volume of all Earth's oceans combined, and it has been in contact with the rocky seafloor below for potentially billions of years. On Earth, the discovery of hydrothermal vent ecosystems in the deep ocean revolutionized our understanding of life's limits. Entire communities of organisms, tube worms, chemosynthetic bacteria, shrimp, crabs, thrive in complete darkness under crushing pressure, sustained entirely by the chemical energy from volcanic vents on the ocean floor. No sunlight required, no photosynthesis, just chemistry and heat. Europa may have the same thing, a dark, pressurized, chemically rich ocean with hydrothermal activity at its floor, sitting there in the outer solar system, potentially harboring life for billions of years without anyone ever knowing. Europa Clipper will make dozens of close flybys of the moon, mapping its surface, analyzing material ejected from its interior through plumes that breach the ice shell, characterizing the depth and salinity and chemistry of the ocean below. It will not land. It will not drill through the ice, but it will give us the information needed to plan a future lander mission that might do exactly that. If life is found on Europa, even microbial life, even the chemical traces of ancient life, the implications for everything we have been discussing in this video would be seismic, because it would mean that life arose independently in two places within our own solar system. And if it arose twice here, in a solar system with only one clearly habitable planet, the implication for the broader universe becomes almost overwhelming. Life would not be a cosmic fluke, it would be a cosmic tendency, and the Fermi paradox would sharpen into something even more urgent and even more mysterious. The Dragonfly mission, also from NASA, is headed to Titan, Saturn's largest moon, a world with a thick nitrogen atmosphere, rivers and lakes of liquid methane, and complex organic chemistry driven by sunlight interacting with atmospheric gases. Dragonfly is a rotorcraft lander, essentially a drone the size of a small car that will fly between different sites on Titan's surface, sampling the chemistry and searching for signs of prebiotic processes. It is scheduled to arrive at Titan in the mid-2030s. Titan is not considered a strong candidate for life as we know it. The temperatures at its surface hover around -179 degrees Celsius, far too cold for liquid water at the surface. But it is the closest thing in our solar system to a primordial Earth, rich in the organic compounds that preceded the emergence of life here. Understanding its chemistry could illuminate the path from simple chemistry to biology in a way no laboratory experiment can replicate. And then there is Mars, The ongoing work of the Perseverance rover, drilling rock cores from an ancient river delta in Jezero crater and caching them for eventual return to Earth, represents the most ambitious sample return mission in the history of planetary science. The Mars Sample Return Campaign, a joint effort between NASA and the European Space Agency, aims to bring those cached samples back to Earth in the early 2030s, where they will be analyzed by every sophisticated instrument our civilization can bring to bear. If those samples contain biosignatures, chemical or structural evidence of ancient microbial life from a time when Mars had liquid water and a thicker atmosphere, more than 3 billion years ago, the consequences for our understanding of life in the universe would be transformative. And if they contain nothing, if Martian rocks are as sterile and lifeless as they appear, that too is data, crucial data about the rarity of life and the specificity of conditions required for its emergence. Every one of these missions is a probe sent into the question of whether life is common or rare, and every answer, whatever it turns out to be, will reshape how we think about the silence of the cosmos and the future of our species. Now let's talk about what is happening at the frontier of propulsion research. Because beyond the conceptual work we discussed in Part 7, there are actual programs with actual hardware and actual testing happening right now. NASA's Glenn Research Center in Cleveland, Ohio, has been conducting ongoing research into advanced propulsion concepts under its evolutionary xenon thruster program and its work on Hall-effect ion drives. Ion drives, which accelerate ions to extremely high velocities using electric fields, have already been used successfully on several spacecraft, including the Dawn mission that orbited both the asteroid Vesta and the dwarf planet Ceres. They are far more fuel efficient than chemical rockets, and while their thrust is extremely low, too low for rapid acceleration, they can operate continuously for years, gradually building up velocities that chemical rockets cannot sustain. The Dawn spacecraft demonstrated that an ion drive could propel a spacecraft to velocities of around 11 kilometers per second relative to the Sun after years of continuous operation. That is still glacially slow by interstellar standards, but it validates the technology and the operational approach. Future iterations of ion drive technology, powered by larger solar arrays or nuclear reactors, could achieve significantly higher terminal velocities over decade-long operation. NASA's Nuclear Systems Office is actively developing radioisotope power systems and fission surface power technologies that could eventually be adapted for nuclear electric propulsion, using a nuclear reactor to generate electricity, which then powers an ion drive. The specific impulse achievable with such a system would be vastly superior to chemical rockets, and the continuous operation enabled by a nuclear power source would allow gradual but relentless acceleration over timescales of years to decades. None of this gets you to the stars in a human lifetime, but it gets you to the outer planets faster. It gets you to interstellar precursor distances, hundreds of astronomical units from the Sun, in timeframes of decades rather than centuries. And every mission that pushes our hardware further into deep space teaches us something irreplaceable about the environment out there, about the radiation, about the dust, about the magnetic fields and particle streams that an interstellar probe would have to survive. Each of these missions is a rehearsal, a deep space training exercise for the technology and operational knowledge that will eventually, in some form, point outward toward the stars. There is also something happening in the private sector that would have seemed implausible even 15 years ago. The commercialization of space access, driven primarily by SpaceX, but also by Rocket Lab, Blue Origin, and a growing ecosystem of smaller launch companies, has fundamentally changed the economics of getting things into orbit. The cost of launching a kilogram to low Earth orbit has dropped by a factor of roughly 10 over the past decade. That trajectory, if it continues even partially, will open up mission profiles that were previously economically impossible. SpaceX's Starship, the largest and most powerful rocket ever built, currently in active development and testing, is designed to be fully reusable, carrying up to 150 metric tons of payload to low Earth orbit per launch. If it delivers on its design specifications and achieves the rapid reusability its designers intend, the economics of space access will change again, dramatically. Missions that previously required choosing between scientific objectives because the launch cost demanded strict prioritization could become far more achievable. None of this takes us to the stars, but it takes us to the point where building and launching the infrastructure for serious interstellar precursor missions, probes sent toward the heliopause and beyond, solar sail demonstrators, advanced nuclear propulsion testbeds, becomes economically and practically conceivable within the next few decades. The interstellar probe concept, studied extensively at the Johns Hopkins Applied Physics Laboratory with NASA funding, proposes launching a spacecraft to a distance of 1,000 astronomical units from the Sun, roughly 25 times the distance of Voyager 1's current position, within 50 years of launch. At that distance, the probe would directly sample the interstellar medium, measure the properties of the local bubble of hot gas our solar system sits within, and return data that no instrument has ever collected. It would not reach another star, but it would be the first mission designed from the outset to operate in true interstellar space, and the engineering lessons from building and operating it would be invaluable. There is something I want to draw your attention to in all of this, a pattern that I think is one of the most important things to understand about where we stand right now. Every mission I have just described, Webb, the extremely large telescope, Europa Clipper, Dragonfly, Mars Sample Return, the Interstellar Probe, Advanced Propulsion Testbeds, every single one of them extends human reach without moving a single human body. We are building right now a civilization whose senses extend across the solar system and into the interstellar medium, whose eyes can resolve the atmosphere of a planet 4 light-years away, whose ears, our radio telescopes and gravitational wave detectors, can hear the collision of black holes 1 billion light-years distant. We are becoming, instrument by instrument and mission by mission, a species with cosmic scale perception. That is not a consolation prize for the inability to travel to the stars. That is a genuinely extraordinary development in the story of intelligent life on this planet. For all of human history until the 20th century, our direct knowledge of the universe extended only as far as our eyes could see from the surface of one small world. Now we have instruments orbiting the Sun, instruments orbiting Mars, instruments on the surface of Mars, instruments heading toward Jupiter and Saturn and the edge of the solar system, instruments in space so precise they can detect a change in distance 1/10,000th the diameter of a proton. We are extending our reach in every direction simultaneously, and the knowledge flowing back from that extended reach is changing us, changing how we see ourselves, changing what questions we can ask, changing what we think is possible. Here is the question I want to leave you sitting with as we head into the final section of this video. What does it mean to be the generation that is alive right now? At this specific and unrepeatable moment, when we are just beginning to read the universe at this level of depth and precision, when the first images from the James Webb Space Telescope are still less than a few years old, when the first gravitational wave detection is within the memory of adults who were alive to see it announced, when the first image of a black hole is a photograph some of us can remember seeing for the first time. We are the generation that gets to experience these firsts. We are living through the moment when humanity's understanding of the cosmos makes one of its great leaps forward. Not incrementally, not gradually, in years and decades that will be remembered for as long as our civilization survives. That is an extraordinary thing to be part of. Not because we did anything to earn it, but because we are here, paying attention, asking questions, caring about the answers, and caring, genuine, deep, intellectually honest caring about the nature of reality is not a trivial thing. It is, as far as we know, one of the rarest phenomena in the universe. In part 10, the final part of this video, we are going to bring everything together. The barriers, the science, the philosophy, the wonder, the frustration, the beauty. We are going to answer the question that has been underneath this entire conversation since the very first sentence. Not can we travel to the stars. We have explored that honestly and at length, but something deeper. Something that I think is the real question this topic is always really asking. Under all the physics and the mathematics and the engineering, what does it mean to be a conscious, curious, mortal creature in an infinite and mostly unreachable universe? And how do you live well and fully and meaningfully in the face of that? Because I think the stars and our inability to reach them have something profound to teach us about what it means to be alive right now, on this one world, in this one moment, with the people around us and the sky above us, and the impossibly vast, impossibly beautiful cosmos stretching away in every direction without end. There is a word in Japanese, mono no aware, that does not translate cleanly into English. The closest approximation is something like the bittersweet awareness of impermanence, the particular kind of beauty that comes not despite the fact that something will end, but because of it. The Japanese aesthetic tradition applies it to cherry blossoms, those flowers that bloom for only a week or two before falling, and to the way a piece of music is made more beautiful by the knowledge that it will finish. The ending is not the tragedy. The ending is what gives the beauty its weight. I have been thinking about that word throughout this entire video, because I think it captures something essential about the relationship between human beings and the stars. The stars are unreachable. We have established that honestly and at length. Not easily reachable, not reachable with current technology, but genuinely, fundamentally, almost certainly permanently unreachable in the physical sense, at least at scales that matter to individual human lives, and perhaps forever. The distances are too vast, the speed of light too absolute, the energy requirements too astronomical, the time too enormous, and yet, every clear night, in every culture that has ever existed on this planet, human beings have gone outside and looked up and felt something. Something that is not adequately described as mere curiosity, something closer to recognition, as if the stars were not foreign objects in an indifferent sky, but something more intimate. Something almost like memory. What is that feeling? Where does it come from, and what does it tell us about how to live? Let me offer you a thought that I find genuinely moving and that I think is scientifically defensible rather than merely poetic. Every atom in your body was once part of a star. We have said this before, but I want to go deeper into what it actually means. The hydrogen in your body, roughly 60% of your atoms by number, was forged in the first 3 minutes after the Big Bang, nearly 14 billion years ago. It drifted through space for billions of years before gravity gathered it into molecular clouds, which collapsed into stars, which burned and died and scattered their contents back into the void. Your hydrogen atoms may have cycled through several generations of stars before finding their way into the molecular cloud that became our solar system. The carbon that forms the backbone of every biological molecule in your body, every strand of DNA, every protein, every cell membrane, was synthesized in the cores of red giant stars through a process called the triple alpha reaction, where 3 helium nuclei fuse into a single carbon nucleus. This process requires a very specific resonance in the carbon nucleus, an energy level that sits at almost exactly the right value to make the reaction efficient. The physicist Fred Hoyle predicted this resonance must exist before it was measured, because without it, carbon could not be produced in sufficient quantities for life to exist. And here we are, so it must exist. When it was confirmed by experiment, it was one of the most dramatic moments in the history of nuclear physics. The universe appeared, in some sense, to have been calibrated for the possibility of carbon-based life. The oxygen you are breathing right now was forged in massive stars and scattered by supernovae. The calcium in your bones came from the same explosions. The iron in your blood, as we said at the beginning of Part 8, was forged in stellar cores and ejected into space when those stars died. The gold in any jewelry you might be wearing was almost certainly produced in the collision of 2 neutron stars, the most violent event in the known universe after the Big Bang itself. An event that the LIGO and Virgo gravitational wave detectors actually observed and confirmed in 2017. You are not made of ordinary stuff that happens to live near stars. You are made of stellar material that has temporarily organized itself into a pattern complex enough to be aware of its own origins. The iron in your blood once burned in a star's core. The carbon in your DNA once floated in an interstellar cloud. The hydrogen in your cells has been part of the universe since the very beginning. When you look up at a star, you are not looking at something foreign. You are looking at a relative, a distant, enormous, ancient relative, but a relative nonetheless. You share the same raw material. You are part of the same story. The stars are not unreachable because they are alien to you. They are unreachable because they are so vast and so far that the same physical laws that built you cannot bridge the gap within any time frame that fits inside a human life. But the connection is real. The kinship is real. And no distance, however incomprehensible, can undo the fact that you and every star in the night sky emerged from the same primordial fire. Now, I want to talk about something that does not get discussed enough in conversations about interstellar travel. Something that the physics and the engineering and the mission planning all tend to crowd out. The question of what we would actually be doing when we got there. Imagine for a moment that all of the barriers were solved, that some revolution in physics opened a path, that a ship could be built and crewed and launched and arrive at a planet orbiting another star within a human lifetime. The people who stepped off that ship onto alien ground would be the most extraordinary explorers in the history of our species. They would be standing on a world that no human eye had ever seen up close. Breathing or not breathing, an atmosphere that had never been contaminated by terrestrial biology. Looking up at a sky lit by a different sun, what would they feel? I think they would feel small. I think they would feel awe so overwhelming it would be difficult to speak. I think they would feel, and this is the part that I find most interesting, profoundly aware of home, of the pale blue dot they left behind, now so far away that even the sun was just another star in the sky. I think they would feel the weight of every person who had ever lived and never known that other worlds existed. Every child who had ever looked up and wondered. Every scientist who had ever dedicated a life to pushing the boundary of knowledge one small step further. They would feel, I suspect, not triumph, not conquest, something more like gratitude, like being entrusted with something immeasurably precious, the first human perception of another world, on behalf of every human being who ever lived and never got to be there, and then they would begin to explore, and the questions would multiply faster than the answers, as they always do, as they always have, as they always will, because that is what the universe does. It does not reward curiosity with finality. It rewards curiosity with better questions. Every answer opens into a vista of new unknowns, deeper and stranger and more beautiful than the ones that came before. The cosmos is not a puzzle to be solved. It is a conversation to be continued. Let me tell you about a moment in the history of exploration that I think is relevant here. Not a space mission. Something older, in 1492, when Christopher Columbus made landfall in the Caribbean, and I mention him not to celebrate the brutal colonialism that followed, which deserves its own honest reckoning, but to note the navigational act itself. He did something that had been considered impossible by the conventional wisdom of his time. He crossed an ocean that most educated Europeans genuinely believed could not be crossed, not because of the distance alone, but because the prevailing theory held that the ocean was too vast, that the food and water would run out, that the currents would strand any ship too far from land to return. He was wrong about almost everything except the basic navigational act. He thought he was in Asia. He had no idea of the actual size of the Earth. He stumbled into a world he had no conceptual framework to understand, and the civilization he represented subsequently did terrible, irreparable harm to the people already living in the world he had found. But here is what I take from this, stripped of the political context. The barrier that seemed absolute, the uncrossable ocean, turned out not to be a barrier of physics, but a barrier of technology and will and knowledge. The ocean did not change, the currents did not change. What changed was the ship design, the navigational tools, the accumulated knowledge of winds and stars, and the organizational capacity to mount and supply the expedition. Most of the barriers we have described in this video are more fundamental than the Atlantic Ocean. The speed of light is not a matter of better ship design. The rocket equation is not going to yield to mere cleverness. I am not suggesting that interstellar travel is simply waiting for our equivalent of a better caravel, but I am suggesting this. Every generation that has ever lived has had things it believed to be permanently, fundamentally impossible. Flight, splitting the atom, reaching the moon, decoding the genome, detecting gravitational waves from 1 billion light years away. Every single one of those things was not just difficult but widely considered by informed, serious, intelligent people of its time to be either impossible or so far beyond reach as to be meaningless to discuss, and every single one of them happened. I am not predicting that interstellar travel will happen. I am not even suggesting it is likely within any time frame I can specify. What I am saying is that the history of human knowledge does not support confident declarations of permanent impossibility. The universe has surprised us before. It will surprise us again. So where does that leave us? You, sitting here, watching this video, alive right now on this one small world in the outer arm of one ordinary galaxy among 2 trillion. I think it leaves us with a responsibility, not a heavy, crushing responsibility, the kind that immobilizes rather than motivates, but the lighter, more energizing kind, the responsibility of being aware. We are, as far as we know, the universe's way of knowing itself, the only matter in the cosmos that looks back at the whole and wonders, the only arrangement of atoms that asks where all the other atoms came from. That capacity, that awareness, is not a given. It is not guaranteed. It is not permanent. Stars will keep burning whether or not anyone is watching. Galaxies will keep colliding whether or not anyone ever develops the mathematics to describe them. The universe does not need us to be aware of it, but we are. And that is staggering, and the least we can do, the very least, is take that awareness seriously, to use it, to point it at the sky and the microscope and the page and the equation and the face of another person, and bring to all of those things the same quality of attention, the same refusal to look away from what is difficult and beautiful and strange. The real reason interstellar travel is impossible, at least today, at least for now, at least in the physical sense of bodies crossing those distances, is not ultimately a failure of technology or will or funding or imagination. It is the simple, magnificent fact that the universe is bigger than we are, older than we are, more complex than we currently understand. It exceeds us. It exceeds our instruments and our mathematics and our most ambitious engineering and our most expansive imagination. And that excess, that overflow of reality beyond our current capacity to comprehend or traverse it, is not something to mourn. It is the guarantee that there will always be more to discover, always more to learn, always more reasons to get up in the morning and look up at the sky and wonder. A universe that fit neatly inside human understanding would be a universe not worth exploring. The fact that it does not, that it keeps unfolding beyond every horizon we reach, that every answer produces 10 new questions, that is not a design flaw, that is the whole point. We started this video with a wall, the wall of distance, the 41 trillion kilometers to the nearest star, and what that number actually means when you sit with it honestly. When you stop using it as a trivia fact and start using it as a genuine measurement of the gap between here and there. We walked through the rocket equation and its iron logic. We looked at every propulsion concept our civilization has seriously explored. Chemical, nuclear, antimatter, light sails, laser arrays, and measured each one against the distance honestly. We explored special relativity and the speed limit built into the fabric of space-time itself. We sat with the exotic geometries of warp drives and wormholes and confronted the requirements they impose, the negative energy, the exotic matter, the engineering challenges that exceed anything our civilization can currently conceive. We looked at the unknowns, dark matter, dark energy, the incompleteness of our physics, not as obstacles but as invitations, as the universe's way of telling us that the map is not finished, that the territory extends beyond the edges of what we have drawn. We thought about what it would mean to actually send human beings across those distances, the generation ship and its extraordinary, heartbreaking demands, the ethics of creating a crew that cannot consent to the mission, the psychology of living and dying in transit, never seeing the destination, the genetic and biological challenges of maintaining a viable human population in a metal tube for centuries. We looked at the Fermi paradox and its unnerving silence, the great filter and where it might sit in the story of life in the cosmos, the rare Earth hypothesis and what it might mean if complex life is not just uncommon but genuinely vanishingly rare. We explored the cutting edge of current research, the laser sails and nuclear drives and antimatter concepts and quantum vacuum physics, and sat honestly with the gap between what we are doing and what we would need to do. We looked at the extraordinary missions being built and launched right now. Webb, the extremely large telescope, Europa Clipper, Dragonfly, the Interstellar probe, and recognized them for what they are. Not second-best substitutes for going there. A genuine, unprecedented civilization-scale extension of human perception into the cosmos, and we looked inward at what the stars are made of and what we are made of, and what it means that those two things are the same, at what it means to be conscious and curious and mortal in a universe this vast, at the cosmic perspective and what it does to the texture of a human life when you genuinely let it in. Here is what I want you to take away from all of this. Not a conclusion, not a verdict, something more like a way of standing in the world. The stars are unreachable, and you are made of them. Hold both of those things at the same time. Let them exist together without resolving the tension, because the tension between them is not a problem to be solved. It is the human condition, stated at its most cosmic and most precise. We are creatures of finite reach and infinite curiosity. We live for decades in a universe that has existed for billions of years and will exist for trillions more. We can see 100 billion galaxies, and we cannot leave the one solar system we were born in. Not really, not yet, not at any scale that changes the fundamental fact of our confinement to this one extraordinary, fragile, irreplaceable world. And that confinement, rather than diminishing us, may be the thing that makes us most fully ourselves, because everything we love is here. Every person who has ever mattered to you, every piece of music that has ever moved you, every meal that has ever felt like home, every moment of genuine connection and meaning and joy, all of it happened on this pale blue dot, not in spite of its smallness. Because of it, the proximity of the people we love, the weight of our history, the shared language and culture and memory that makes human community possible, the fact that we are all always neighbors on a world small enough that our actions reach each other, these are not things to escape, they are things to cherish. Things made more precious, not less, by the knowledge of what surrounds them. The vast, cold, silent, beautiful, unreachable universe does not diminish Earth. It frames it. It gives this one small world, with its liquid water and its oxygen atmosphere and its billions of lives and its 4 billion-year story of increasing complexity and its very recent and very remarkable development of awareness. It gives all of that a context that makes it luminous. We will keep trying to reach the stars. Of course we will. Because we are the species that cannot look at something and not wonder, that cannot identify a barrier and not begin immediately working on ways around it, that cannot accept a limit without asking whether the limit is final or merely current. That is not a flaw. That is our defining characteristic. The thing that has taken us from caves to the moon in an eye blink of cosmic time, and someday, in decades or centuries or millennia, by means we can barely imagine from where we stand today, something we built, or something we sent, or perhaps something that carries the information of what we are, will cross the distance, will bridge the void, will arrive at another star and look back across the light years to the place where everything we know began, and when it does, it will carry something of you. Not your body, not your name, but the curiosity that made you watch this video, the wonder that made you care about the answer, the awareness that made you look up at the night sky and feel something you could not quite name but could not quite dismiss. That feeling, that ancient, wordless recognition, is humanity's most important export, more important than any probe or signal or biological blueprint we might transmit across the void. It is the universe knowing itself. It is the cosmos, after 14 billion years of silence, finally finding a voice. And that voice is yours. The stars are out tonight. Go look at them, not as points of light, not as navigational markers or mythology or the setting for someone else's story. Look at them as what they are. Nuclear furnaces 100 times the size of our sun, burning through billions of tons of hydrogen every second, pouring light across distances so vast that the light you are seeing left its source years or centuries or millennia before you were born. Look at them as your ancestors, your raw material, the furnaces that built every atom of the body you are using to look at them as your horizon, the unreachable edge of a territory so large that it will never stop demanding more of us, more curiosity, more courage, more imagination, more honesty about what we do not know, and then look down at the ground beneath your feet, at the world around you, at the people in your life and the one irreplaceable, unrepeatable existence you have been given on this tiny, luminous, extraordinary world. The real reason interstellar travel is impossible, at least for now, at least for us, is that the universe is so much larger than we are, but we are large enough to know that. And knowing it, if you let it in all the way, changes everything. That is not nothing, that is everything. And if this video left you staring at the sky, wondering just how far we've actually managed to send something, you need to watch this next one. Voyager 1 is out there right now, drifting beyond our solar system, and it is going to keep going long after every human alive today is gone. Click the video on your screen. You will not regret it.